Sasha, you're muted.
Yeah, it's okay. I'm just talking here.
Okay.
Саша, привет.
О, привет, привет. Спасибо, Миша.
Ситуация развивается.
Очень хорошо. Жалко, что не на кампусе.
Ну да, да.
Но
видишь,
мы это наверстаем, мы наверстаем.
Я думаю, да. Слушай, да я попробую. Или попробовать, но я думаю, нормально все будет. Зашерить или нет.
David, let's try and so that Misha can share his screen.
Just let me try for 1 minute.
Mm-hmm. Yep.
Does it look good? Okay.
Мы вчера с Кузьминым тебя вспоминали.
Ага. А что, ну у вас тоже был, что ли?
Был. До сих пор отходим.
Да. А он у него тур, что ли? Он у нас был, когда тоже в понедельник.
У него же сын градуировал из Пердью, поэтому.
Да.
С нашего департамента.
Они были в Бостоне в понедельник. Мы
Да.
с ними
Он сказал, что вы отметились, да.
Да. Они были все вместе, да, с женой, как бы.
Да. Я до сих пор болею.
You guys have to start speaking English again. With a southern drawl would be great.
No, David, no. Come on.
Sorry. You folks, by the end of this center, you should all speak Russian with us.
I don't know if David's, leadership appreciated,
Well, if we really want to be diverse, I've got to learn Russian. That's going to be hard.
That's it. Yeah, that's the point.
Are you guys ready? Is it nearly time? How is this working, Sasha?
I think we are nearly ready.
All right.
So shall we start now? All right. Okay. Hello, everyone. Thank you for joining the first session for the Quantum Science Center Summer School. I'm Xiaohui Xu from Purdue, and I'll be moderating today's session. So today, we will first have opening remarks from Dr. Devin Dean and also Professor Alexandra Borisova. And I think, first of all, we'll start with Dr. David Dean, the director of the Quantum Science Center. So David, whenever you're ready.
Sure. So welcome. I see we have about 40 people, probably going up in a few minutes, a little bit. Welcome to the first Quantum Science Center Summer School. This is the Quantum Science Center is one of the 5 U.S. Department of Energy quantum information research centers, quantum information science research centers. And our 5-year mission is really to, I would say, unblock and help make quantum computing, quantum sensing, quantum algorithms space grow. And I think in that sense, we're also working toward workforce development efforts, and this is one of them, to have a summer school, which is really a great thing. You know, in thinking about what to say here to you as a welcome, I thought about my own experiences as a student. And in 1988, which seems to be a long time ago now, I actually went to a summer school in Corvallis, Oregon, as a third-year graduate student entering the fourth year. And it was the first national nuclear physics summer school at that time, the first, number one. And it was really great. I met people there that I became colleagues and friends with across my entire career. And that was really a great experience. I actually wrote articles with a couple of the people who spoke at the event. I presented some of my own R&D, and I just got to know a lot of good people. And so, you know, that's one of the aspects of the summer school that we hope happens. Now, we know we're online. We know we're not there in person. But I believe this is one of the big promises of a summer school, to be able to connect you all with both speakers and with each other, so that in the future of your careers, you'll kind of get together and be able to do great things together. Interestingly, in 1996, I actually taught at one of the same summer schools. It was the 8th one at that time. And in 2003, I organized one for that series. It was the 15th one. And then in 2004 to 2007, I was the chair of the organizing committee, the committee that steered that effort. And then I spoke again in 2015. So that particular summer school became a lifelong effort, so to speak. And that's why when we wrote the proposal, we were obviously going to have a summer school. And I think having somebody like Sasha and the Purdue group involved in the QSC has been extremely useful in this sense, because of the character and nature of the students there at Purdue, and because of the organizational capabilities that are with us through Purdue. And so it's a no-brainer. I'm glad you're here. I hope you guys have a great time. I will listen to a few of the talks off and on. And on Thursday, I think there's a panel session, which actually I will be out of town. So actually, Travis Humble is going to oversee at the end. So he's our deputy director for the center. So we're really excited, and we hope you all have a great time and learn a lot. Don't be afraid to ask questions. Don't be afraid to make mistakes, and enjoy. And so, Sasha, I'll hand it over to you.
Yes, thank you very much, David. Well, and thank you all for joining. So I'm Sasha Boltaseva, I'm professor of Purdue, and I'm workforce development lead at the Quantum Science Center. So first of all, on behalf of the Quantum Science Center and Purdue Quantum Science and Engineering Institute, I am so excited about this school. We have absolutely outstanding speakers lined up for this week. We have over 400 registered participants. Now we are a little bit over 50, but we will get more, I'm absolutely sure. And we are streaming it live on YouTube. Well, first of all, I know usually we say thanks at the end of the event, but I would like to extend my thanks to the whole team who actually put this together. And when we started the workforce development activities at the center, we immediately said that it has to be driven by students and postdocs. And largely, it is driven by students and postdocs. And my special thanks for the team of moderators and the students and postdocs involved in the school who actually helped greatly to put this all together. And this team is led by Alex Senichev, who's been extremely instrumental and important for putting this together. Many thanks to Managing Director of Purdue Quantum Science and Engineering Institute, David Stewart, and our administrative angel at the Quantum Science Center, Erica Valentine, and the whole workforce development team. We do believe, as David already said, that one of the most important things for people at any career stage is networking. And even though we are virtual, we do hope that you will connect to your mentors, your senior team members, to our speakers, and to your peers. So with that, I guess let's just get started. We have such an exciting program ahead, and I am really looking forward to every single talk that we're going to hear this week. So we are streaming live on YouTube, as I already mentioned. And I guess with that, I will hand it over back to Xiaowei, who will be introducing our very first, very honorable speaker. Looking forward to that.
All right, thank you. Thank you, Sasha and David, for the very exciting opening remarks. So next we have two interesting talks. The first one will be from Professor Mikhail Lukin from Harvard, and he is the George Vassman Labrat Professor of Physics. And the title is The New Frontier of Quantum Science and Engineering. So if you have any questions, I would recommend you to either type in the Q&A channel or in the chat channel, and we'll try to address them at the end of the talk. So Professor Lukin, please.
Thank you very much for a kind introduction. And I feel really honored to give the very first talk at this, very special summer school, which I hope will become a tradition for many years to come. So let me just start kind of at a high level, so I guess, what we do in our world is we are trying to develop this new field of quantum science and engineering, which we view as a quest for controlling quantum world. So in this quest, what we are trying to do is we're trying to isolate and control simple quantum objects and build more and more complex systems from them. And with that, we hope to really explore new frontiers of science with this kind of engineered many-body quantum systems, like create and probe new states of matter, but also explore new applications. And applications are quantum processing, communications, and metrology. And this field, despite all of this excitement, despite all of these new centers which appear, kind of quantum centers which appear nearly daily, faces two big challenges. One is the challenge of building large-scale quantum systems. Right now, we do not know if and how we can build, for example, truly large-scale quantum computers. And then another challenge is that even if you build one of these computers these days, you wouldn't actually know exactly what to use it for. And this is what I call quantum application challenge. How can we apply these machines to achieve useful quantum advantage? So in this field, we are kind of often talk about quantum rivalries. So it could be rivalries between different physical platforms, between different countries, or between different quantum centers. But the actual rivalry here is really between two contradictory forces of nature. One of the force is a controllability to really, kind of make use of the quantum phenomena for interesting applications. We really need to control qubits, at an unprecedented level, one by one. But another one is scalability, right? We will need to have large number of those. And these two forces of nature are, often do not like to coexist together. So basically, this is not only true in quantum world, it's also true in classical world, even in the social interactions. If you have a large group of very smart people, it becomes very difficult to control. But in the domain of quantum physics, this is definitely an outstanding challenge. And basically, where the field is, we would like to kind of build big enough, programmable enough, and coherent enough systems such that we can really gain access and control systems of more than 100 quantum bits. And with this, we hope to gain some knowledge to build even bigger and better quantum machines, and also start addressing this algorithm and application challenge. And what I hope to convince you by the end of my talk, we're already entering this very interesting kind of domain, or the world, if you want, where actually no one has ever been. So it's kind of like a part of the, we can create states no one has ever created. And so this, in doing that, we really have an opportunity to start kind of discovering new things. And so for this reason, I like to call this, what's happening now is the age of quantum discovery. So in thinking about what to do, I was actually somehow, was wondering what can I do, what kind of talk can I give, which would somehow try to cover the broad range of scientific activities that you guys are planning to undertake in your center, ranging from optics all the way to topological qubits, and also do it in a way which is a little bit kind of tutorial. So I decided to focus, basically on, one set of projects in our lab. And this is a project involving building scalable quantum systems using Rydberg atom array. So I'll tell you how we can use basically laser beams, steerable laser beam, to build, systems, atom by atom, and, systems which are as large as, 300 qubits, and how to control such systems. And, I will also then tell you about some ongoing work in our labs to use the systems as programmable quantum simulators. So in particular, I will tell you a little bit how we can explore phases and phase transitions in two-dimensional spin models. But then, as a kind of outlook, what I'd like to do is I'd like to turn the attention to topological physics and actually describe you some of our very recent work involving the first realization of something which is called topological spin liquid. This is basically a long sought state of matter, which is a basis for topological qubits. And I will tell you a little bit about our work building a baby kind of qubit, and I'll come back then with the ideas of towards scaling up and show again how kind of modern optical techniques can really allow us to push forward this system. So during my talk, please feel free to ask any questions, and I will actually moreover make two stops in the middle of the talk to kind of enable the discussion. Okay, so in this talk, we will be focusing on discussing quantum processors based on individual cold neutral atoms. And those systems have some obvious advantages. For example, they feature excellent coherence properties. For example, modern optical clocks are based on neutral atoms. And it's also very easy to create large number of neutral atoms. So for example, in each of our room, there are a lot of atoms and molecules flying around. So in principle, if you could somehow track every one of them and control every one of them, you would have a big quantum computer at your disposal. But there are also some challenges in doing that. And there are two maybe key challenges in this field. One is that atoms in the gas phase typically interact very weakly with each other. And moreover, atoms neutral atoms in particular are very hard to control individually, at least in large numbers. So that's kind of, this idea that you can somehow trace as atoms as they fly around, it makes it almost impossible to think about any kind of, realistic application of this approach. So motivated by this consideration, a few years ago, we started to think about new approach to build to building quantum systems. And in particular, what we wanted to do is we wanted to address this individual control challenge. And our approach is based on the optical techniques, in particular on something which is called optical tweezers. So basically, what's optical tweezer? So if you take a beam of light and focus it very sharply, then what will happen is that this beam will actually start attracting, any objects with which have some finite polarizability. So basically, and these particles will typically be attracted to the point of highest intensity, which is basically the focal point. And since individual atoms have some finite polarizability, you can use this approach to basically trap individual atoms. And that's the basis for something which is called optical tweezer, the technique which exists now for several decades. And so what we do in our approach is we start with the gas of the atoms, which is slowed by conventional laser cooling technique. And then what we do is it happens in a vacuum chamber. And then basically in this vacuum chamber, we shine typically not just one focused beam of light, we shine hundreds of these beams. And each of these beams we focus so tightly that it basically can accommodate at most one atom. So basically it turns out that if more than one atom is captured, then these two atoms just cannot fit into such a tightly focused tweezer, and they just get ejected. And so in practice, then what happens is that, on each approach, we try to load these optical tweezers, and we end up with a set of traps, some of which are filled by one atom and some are empty. So the system like that has some entropy, and we get rid of this entropy by simply taking a picture of these loaded atoms, figure out which traps are full and which are empty, and then basically eliminate the empty trap and then kind of rearrange the rest of the atoms in a kind of desired geometry. So with that, we end up with the system of individual atoms prepared in well-defined internal states, which are typically separated by few micrometers. And such system is completely classical. These atoms do not interact with each other. The interaction is negligible. So to induce the interaction, what we do is we excite these atoms into the states with high principal quantum number. So these are the so-called Rydberg states. And in this kind of Rydberg states, the atomic size grows dramatically, and then the atoms really start, feeling each other as present. And that way, we can enable, highly programmable, coherent quantum mechanical interactions between the atoms. And this is the basis for our joint project together with my colleagues Markus Greiner and Vladan Vuletić. So as I already mentioned, so Rydberg atoms, play a central role in this. So this is just kind of a reminder from the Quantum Mechanics 101. So basically, if you take hydrogen atom and put them, or hydrogen-like atom, and put it in a state with large n, what happens is that its size grows quadratically with n, and for n equals 100, it's actually becomes a fraction of the micrometer, and so at the same time with this large object, you also have some very high polarizability. So it means that if you apply electric field, the object becomes very easily polarized, and as a consequence, then there is also very strong interaction between these two Rydberg atoms. So basically, the interaction scales as 11th power of principal quantum number, and for n equals 100, the interaction, the van der Waal interaction, is 14 orders of magnitude stronger than between the ground state atoms. So this 14 orders of magnitude is a large number, and we can make a very good use of this kind of interaction. So one way how we can use this interaction is in a phenomenon which is called Rydberg blockade. So what is that? So it is, it can be understood the following. So suppose you have now two atoms which are far away from each other, which you are trying to excite with laser beams into the Rydberg states in a coherent way. So under these conditions, what will happen is that the atoms will undergo independent Rabi oscillations, and they will just not feel each other's presence. However, if you start now bringing this atom closer and closer together, at some point, these interactions between Rydberg atoms will become substantial and actually will take over to the point where if you are still trying to excite atoms resonantly, you will be able to excite one atom or another, but never both. And so, under these conditions, you're entering the regime of the so-called Rydberg blockade, where simultaneous excitation is blocked. So it's blocked at distances smaller than what's called blockade radius. And this, it turns out to be a very effective way to kind of entangle atoms, manipulate their quantum state, because under this blockade, this entanglement mechanism is insensitive to things like motion and position of the atoms. So in short, what we will be doing in our experiments, we will be starting with some disordered arrays and then sorting atoms in a way, that we wish. So creating some regular arrays of the atoms and subjecting them to sequences of laser pulses, and then eventually reading out their, state in a projective measurement just by kind of looking at a state-dependent fluorescence. So, so that's kind of a high-level approach. So, kind of in practice now, and it's kind of very generic, right? So, but in practice, what we can do, we could choose a type of atom that we want to work with, and often these experiments utilize the so-called alkali hydrogen-like atoms. So, for example, I will be showing the results from the experiments involving rubidium atoms. But there is also some effort now to, for example, create atom arrays using alkaline earth atoms like strontium, ytterbium. Then you also, have a lot of possibilities how to encode a qubit in each of the atoms. And so in particular, what I will mostly focus on today is the approach involving what we call ground Rydberg encoding. So basically, where you encode a qubit in the superposition of the ground state and a Rydberg state, where Rydberg state is a state with high n. But alternatively, one can also encode a qubit in the hyperfine states of atoms. And basically, that way you can have a very long lifetime, basically many seconds of the lifetime. And then if you want to turn on the interactions between atoms, you just excite it into the Rydberg state. So these kind of methods can be applied to all sorts of, directions involving quantum computing, quantum simulation, quantum networking, quantum metrology. But I kind of like to think about this approach as basically implementing the original vision of Richard Feynman, who actually was a paper which started this kind of entire field of quantum information processing, where he noted that, basically, if you want to use classical computers, then to model quantum system in general, this will be very hard. So, for example, if you have n quantum bits, then to model the evolution of these n quantum bits, it will require a solution to the 2 to the n coupled equations. And, if n is small, it's, maybe, 5 or 10, you can easily write them down and solve them on your laptop. But when n, starts approaching a number of something like 50, it becomes very, very hard. It's impossible to kind of even store this kind of the information required to solve this equation. So the alternative approach is to basically implement a model of this interacting system, where you can basically build this system from well-controlled elements, and you have some standard set of qubits with programmable interactions. And this is exactly what this approach, which I am kind of describing, implements, right? So you basically can, build a system from individual atoms, position them, engineer interactions, adjust the interactions between them, and then with that, proceed with the time evolution. So what's kind of most natural kind of application of that? The application of that system would be quantum simulations. And if you, for example, start with the one-dimensional chain of the atoms and excite them into the Rydberg state, as shown here, such a system can be described by this fairly simple Hamiltonian, which actually is an Ising type, Hamiltonian. It's just written in a little bit, different way. So n now is here as a number of Rydberg atoms on each side. So it's 0, 1. And you can kind of understand, and so omega is a Rabi frequency of exciting laser, and delta is a laser detuning, and V is the interaction. And so you can understand the physics which this Hamiltonian described by looking at its ground state and its ground state phase diagram. And in particular, you can parameterize it by using two parameters. One is a normalized detuning. So it will act as a kind of chemical potential in this model. And another one is the interaction strength. And so basically, if the interactions are negligible, then the ground state, is totally determined by the sign of this detuning. If this detuning is negative, then all atoms should be in a ground state, right? Because basically you want to minimize this energy of this Hamiltonian, so n should be 0. But if the detuning is positive, then all atoms should be in the Rydberg state, in the excited state. But of course, the state like this is incompatible with blockade. So if you have, any interactions, even just limited to nearest neighbor, you will not be able to reach this kind of state. So basically, if you have, short range interactions, with nearest neighbor blockaded, then what will happen is that the state with most Rydberg atoms you can excite will be the state shown here. This is a state where you basically have up, down, up, down, up, down. So the state satisfies the blockade constraint, and it actually has an order. It's kind of antiferromagnetic order. And this actually state breaks the so-called Z2 symmetry. But if you now increase the range of interactions, the range of blockade even more, then what will happen is you will blockade not just the first nearest neighbor, but also the second nearest neighbor. And so then you will break Z2, Z3 symmetry. Sorry, you will have states up, down, down, up, down, down, and so on. And then this hierarchy continues. So now, how can we probe? So it's actually a phase diagram, which has been already known for this kind of model, for a while. How can we probe it experimentally? It's actually very easy for us to do it. So what we can do is we can just start with all atoms in the ground state, adjust the interaction strength and spacing such that we have only certain number of nearest neighbors as under blockade, and then just try to adiabatically sweep the detuning, from negative to the positive value, and then basically, we immediately, readily, create this state. So this is, some of our first results for this chain of 13 atoms. So where we basically, start with all atoms in the ground state, and here enter into this state, where you have Rydberg atom shown here with the red circle, ground state atom, Rydberg atom, ground state atom. If we now, bring the atoms a little bit closer, then, not only the first neighbor is blockaded, but only a second nearest neighbor. And, basically what you see here is that these programmable interactions result in a desired symmetry breaking. So basically using this approach in the past, couple of years, we actually have really enjoyed a wide variety of opportunities. We have used this approach to, for example, implement high fidelity entanglement and, parallel multi-qubit quantum gate operations. We explored phase transitions in arrays, exceeding 50 atoms. We also studied non-equilibrium dynamics. So that's actually an area which is perhaps most interesting for applications, because if you take quantum system, any-body quantum system, and push it away from equilibrium, it starts evolving in a kind of highly non-trivial way, and actually these phenomena are extremely hard to predict numerically. And in fact, basically every time we did this non-equilibrium experiment, we would discover something new. Then we also use this approach to create a large-scale entangled state. So this is actually a 20-atom GEG state, which was at the time the largest. In fact, the record only was broken just a couple of months ago, where a few more qubits have been entangled. So basically, all of these directions are very closely connected because involve coherent high fidelity, either analog or digital evolution. So maybe at this point, I would like to slow down a little bit and see if there are any questions. So this is was a basic overview of this area, and let me just see if there are any questions about that.
Yes, there are quite a few questions already there.
Okay.
Professor Lukin, can you see them? Maybe I can pick two of them and then leave the rest to the end of the talk.
Why don't you, how about you ask them? I think it's better if you ask somehow. I cannot, I cannot see them all somehow.
Yeah. Okay, so one of the question is about how do the lifetimes of the Rydberg states compared with the lifetime of the hyperfine levels used for encoding qubits?
Yeah, so the lifetimes of the Rydberg states are relatively long. They are typically, for the states we use, they are hundreds of microseconds. And compared to interactions, for example, interaction strengths, they are relatively long. But, of course, they are much shorter than the lifetimes of the ground hyperfine sublevels, which are typically limited by basically how well you, for example, control magnetic fields, how good is your vacuum. So it can easily be, seconds, or even, longer hours, So, and that actually is a kind of very special feature because it allows us to, this hierarchy of lifetimes really allows us to create, to make use of the situations where you can have, for example, very long-lived memory for the qubits on one hand, and also, very strong interaction. So basically, the combination of very strong interaction and a relatively long lifetime, hundreds of microseconds in Rydberg states, allows us to perform high fidelity operations. But at the same time, if you really want to kind of shelve the qubit and store it for some time, then you can use the hyperfine states. And we are starting to use these kind of features, right, in the experiments. We'll maybe not talk about them, but, that's, yeah.
Mm-hmm. I see, thanks. And maybe we have one more question for now. So how to excite atoms into the Rydberg states while keeping them trapped in the tweezer?
Yeah, that's actually also an excellent question. So, and Rydberg atoms generally have very different polarizability from the ground state atoms. And in fact, depending on the color of light that you use to trap atoms, in some cases, and the Rydberg state, in some cases, those Rydberg states will be trapped. In some cases, they will not be trapped. In fact, they can be anti-trapped. So what that means is that in our but actually also if the Rydberg atoms are trapped, then often the trapping potential will be very different. And this actually is a challenge because if you then create a superposition of ground and Rydberg atoms, this superposition will basically undergo kind of motional dephasing. So for these reasons, in most of our experiments, what we like to do is that before we create the arrays and we store our qubits, but during the time when we excite the atoms to the Rydberg state, we actually typically turn the traps off. And this, you would say, well, but what happened with trapping? The atoms will fly away. But so typically this does not happen because we turn the traps off and we do the Rydberg excitation within the time, which is much, much shorter compared to typical kind of motional time scales of atoms. And so, for these reasons, for example, we can basically turn a trap off, excite the atoms, do Rydberg manipulation, bring the atoms back, and then turn the traps on, and basically the probability of atom loss is very, very small under these conditions.
I see. Thanks, Professor. I think we'll save the rest of the questions to the end of the talk.
Okay. All right. Thank you. So we will then proceed. And, what I will talk now about is the second generation of our experiments, which we implemented about a year ago, actually. We implemented a major upgrade in which we can now control two-dimensional atom arrays. And the key part of this upgrade is this device called Spatial Light Modulator, which is basically a computer-generated hologram, kind of diffraction, the kind of the grating, basically, where you can imprint, for example, phase on a light beam, and as a result, basically by kind of reflecting the beam from this SLM, you can, depending on the pattern that you create, you can actually deflect the beam in a kind of different directions, and basically you can create now two-dimensional arrays of traps. And so basically when we image it in a vacuum chamber, we can easily create arrays of hundreds of thousands of traps, as shown here. Now the disadvantage of this spatial light modulator is that actually is very slow to update. So for this reason, we have a second kind of channel, and we have a second set of laser beams which we use to sort the atoms. And this second channel has two devices which are called acousto-optic deflectors, where you basically, by putting in RF tones, you can actually steer these beams and kind of, in this way, you can move the atoms, between different, traps, and basically in this way you can actually sort the atoms, and everything is now, of course, computer controlled. So one other thing which happened is that basically just at the time when we completed our, upgrade, that was kind of the middle of the March. That's, when the COVID shutdown has started. And actually, fortunately, we had about a week of warning. And during that week, we actually were able to convert this experiment into complete remote control. And this is thanks to this amazing group of people, who actually, is responsible for all of this kind of results. So basically, with all of that, we now, for last year, we have been operating this second generation atom array. And so the beauty here in these two dimensions, we can create a wide variety of different lattices, both regular lattices and also random lattices. So for example, if in this case, if we would like to create this randomly filled, pattern, we just program it and then try to create it in the experiment, and indeed it kind of works. And basically, at this point, we start with about 600 traps, and, we have over 50% of filling. So we can create approximately, 300 sorted atoms with kind of a reasonable probability. So what do we do with that? And so the first approach to benchmark it was to basically explore quantum phases and quantum phase transitions that you can basically create in this two-dimensional platform. And again, so this is this Hamiltonian, which I already have discussed. So if we, for example, start in a square lattice, then the simplest phase which we will create will be a two-dimensional antiferromagnetic phase. So this will happen if you have only short-range interaction. So basically, this is a phase which which you will create. So we call it a checkerboard phase because it's basically around the Rydberg atoms, kind of a different color, if you want. But, of course, again, we can start playing with interaction range. And then, it turns out that under these conditions, you can create a wide variety of all different type of phases. And there is actually quite complex phase diagram, which again, you can very easily explore by just, for example, changing the interaction strength and changing the distance between the atoms. So all of these phase diagrams can now be accessed. In fact, we already kind of explored and realized and explored most of these phases. But prior to this work, even this very basic transition from the what's called disordered, from a trivial phase into a checkerboard phase, and this is two-dimensional 2D Ising quantum phase transition, it turned out has never been observed previously. Okay, so how can we study it? So we can study it by by preparing a square array of individual atoms. So that's a picture of individual atoms. And then again, in a spirit similar to what I just described, so we can just start changing the detuning slowly from negative to positive value. And then eventually we should enter the ordered phase. And then we can take the picture of atoms, and indeed, in some cases, we see this perfect antiferromagnetic pattern, across the entire array. So, okay, admittedly, this is not always the case that you have a perfectly ordered pattern. So, how can we quantify it? There are a few ways. So one of them, we can look at the correlation function. So this is this kind of up, down correlation, across and then actually it turns out these correlations, spread across the entire array. We can also look at distribution of microscopic states. So it turns out that actually, most of the states that you create, and there are many of them now, there is basically 2 to the power of number of atoms in total states. Many of them, occur only once. And some occur, twice and 3 times, but actually it turns out that the most probable state is actually, or 2 states are the state of the type shown here, where you have perfect antiferromagnetic ordering, and also another complementary state, which is basically, where the order is just shifted by kind of one unit. So, and, by doing these kind of experiments, we can also, for example, quantify, benchmark how well our system works. So this is the probability to find a perfectly ordered ground state pattern. So it's actually decreases exponentially. But, it kind of from here, we can, for example, estimate the error. And it actually turns out that during entire procedure, including preparation, evolution, and readout, the error per atom is about 3%. But how can we actually, study if, so far this is basically all of these images are classical. How, what are the quantum aspects of this? Is there some quantumness in the system? And actually to do it, we really focused on this Ising quantum phase transition. And it's known from the theory of quantum phase transitions is that basically they can be all placed in different universality class where they are characterized by something which is called critical exponents. And we can study these critical exponents by basically, going across the phase transition with different rate, with different speed. So in fact, if we go quickly, then what happens is that the system does not have enough time to build a correlation. So we build a short range correlation. But if we go slowly, then that's where the correlation spread across the entire system. And actually we can plot, for example, a correlation length. And indeed you see that if you go slowly, you build correlation. But if you go quickly, the correlations builds much more slowly. So basically, the way how to measure this critical exponent is use this idea of universality. So what you should do, you should basically rescale all of this, curve with the speed with which you are going. And then it turns out from this rescaling, you can actually extract these critical exponents. And indeed, what we find is that if we do this rescaling, these curves, collapse on the top of each other, and then by optimizing this collapse, we actually can, extract the critical exponent, which is actually consistent with the Ising quantum phase transition in 2+1 dimensions. And is actually distinct from, for example, classical transitions or from quantum transition in different dimensionality. So this is something that we can really use as a benchmark for quantum many-body dynamics. So with tools like that, over last year, we have actually enjoyed, a wide variety of, of cool experiments. So we explored this two-dimensional phase diagrams. We studied quantum dynamics, and kind of more recently, we were looking into these topological phases and starting to think about this combinatorial optimization and also push the system towards a universal programmability. But before I go into some of these advanced topics, so perhaps I can slow down here and again ask if there are any questions.
Yeah, there's one more related question for this section. So the question is about how much time does it take to set up this 2D array of atoms, and like a brief introduction about the steps involved will be also helpful.
So basically, so these steps I in principle have explained. So what you need to do, you need to first load the atoms in the straps produced by a special light modulator. Then you need to take an image to figure out which straps are full and which are empty. And then, you turn on this second set of tweezer beams, using these acousto-optic deflectors to move them to sort these atoms. Then we typically take another image to see how well our rearrangement, works. So, and then afterwards, we basically start the experiment. So the experiment itself, this Rydberg excitation and evolution is typically quite, is rather quick. It takes, maybe, typically a few microseconds at most, because the interactions are very strong. But this preparation and readout procedure, it is what it takes time. So basically, overall, this kind of rearrangement and taking the images and loading and so on, it takes in total, typically, close to maybe 100 milliseconds. So basically we have, as a result, we have a repetition rate of few shots per second. So this is certainly not optimized. It can be kind of much faster, but only a small fraction of that is actual coherent manipulation. Most of the time is in preparing and actually reading out the result.
I see. Thanks. Yeah, that's the only question I see right now.
Okay. All right. So then I will try to move maybe in somewhat more advanced topic. So okay. So that's there are many applications of this approach from many-body physics to computing and metrology. And so basically what I will try to do in next 10 or 15 minutes or so, focus on one of our most recent experiment where we create and probing so-called topological phases. Okay, so first off, what's it all about? So about 5 decades ago, P.W. Anderson, a very famous condensed matter physicist, postulated the possibility of existence of the so-called quantum spin liquids. So, and basically, what he already kind of at the time was thinking about, that this could be a very special matter, which properties are really determined by the system's topology, right? So you can basically, if you create this phase, you can not destroy it kind of easily. So you basically cannot destroy it by continuous deformation. You need to really, cut somehow the system, right? You need to change the topology. And, this, in particular, this kind of phases of matter, he thought could be really realized in the systems which have something which is called frustration. So imagine that you have, again, a magnetic system where you can, have, spins, for example, in this triangular lattice. And suppose the interaction is antiferromagnetic. So basically, if this spin is up, then, to satisfy this antiferromagnetism, you need to place the near neighbors should be down. So, but the problem here is that if you make this spin point down, so where do you put this other spin here, right? So that's this frustration. So, and basically, kind of starting from this idea, there has been an intense, almost, 5-decade kind of, quest in exploring if states like this can really be, created. And people realize that kind of the most likely scenarios in this case, what will happen is that, these spins here, they will form this kind of singlet bonds. So they are so-called dimers, right? And basically, you could kind of envision the state of matter where these dimers cover, all of these, possible spin configurations. In fact, these gave rise to this idea of resonating valence bond states, where you basically have these dimers, which, continuously, flip-flop between each other, and as a result, create these states, which are basically superpositions of all of these kind of dimer coverings. So basically, this was the work which is done in a kind of condensed matter physics side of things. But actually, about 20 years ago, Alexei Kitaev realized that these ideas of topology and of topological protections can be used to encode and protect quantum information. And that's the basis for this fault-tolerant topological, quantum computing. And, the famous thing which actually he at the time put forward together is this kind of toric code. So basically, those are kind of very strange states because they don't have a local special order. So you can basically not distinguish if the system is in the state or not by just looking locally. So basically, they are kind of superpositions of all of these kind of, dimer, fluctuating dimers. So they basically should have some very large ground state degeneracy. So in order to basically observe and distinguish them, you have to measure some kind of topological operators. And in this case of Alexei, it's basically the so-called, string operators. So basically product of, either X or Z operators, which cover the entire, system, in this case, two-dimensional system. So basically, these are these kind of famous systems which are supposed to feature topological robustness, and, they're the basis for topological quantum computing. But as you guys probably know, there is up to now no conclusive experimental evidence in any systems today if such states can ever be created. And they have not been created up to now. So motivated by this consideration, about a year ago, we started, discussing with our condensed matter colleagues, Subir Sajdiv and Ashwin Vishwana, who thought about this topological matter for a long time, in case of Subir for almost 40 years, if we could actually create such states in our Rydberg system. And in fact, they came up with two ideas to realize some such states, which actually by now we have both implemented. So I'll focus here on this idea from Ashwin Vishwana and his postdoc Ruben, where basically the atoms should be placed on links of the so-called Kagame lattice, or it's also, this arrangement alternatively is called the Ruby lattice. Okay, so what's the idea? Oops, sorry, this was not planned. Hold on. Most interesting part. So, do you see? So, I'll share again. Okay, so what's the idea? The idea is basically the following. So let us, place the atoms on the links of this Ruby lattice, and let us also adjust the blockade radius such that for every excited atom, every atom in Rydberg state, its 6 nearest neighbors are blockaded. So in this case, you will have at most 1/4 atoms excited in a Rydberg state. And you can formally map this kind of model with maximal filling into this dimer model, where basically every Rydberg atom corresponds to the dimer living on a link of this Kagame lattice. And this Rydberg blockade constraint ensures that no 2 dimers touch a single vortex. So basically, they create this so-called dimer covering. So what's a spin liquid state in this case? Well, it should be a superposition of, there should be a macroscopic number of these dimer coverings. And basically, spin liquid should be a superposition of all of these possible dimer coverings. So, so how can one see this? Well, okay, so we can start and do the experiment. So these are the atoms, which are a picture of the atoms which are placed on this Kagame lattice. And when we basically adjust Rydberg blockade appropriately, we, do the adiabatic evolution and then create a state like this, right? And the state, it's roughly consistent with all, dimer, kind of perfect dimer covering. It's not perfect. There are some, sometimes there are some errors. But most importantly is, if you have pictures like this, how do you actually realize, can you think, how can you probe if you're in the topological phase or not? So that's a big question. Okay, so let's kind of look at this state a little bit more carefully. So that's a pulse sequence, which we kind of use. And basically we can look, for example, at average number occupation. And indeed we see that there is this kind of, almost like a plateau around 1/4 filling. But again, there is nothing, super special which happens here, So yeah, it's true that there is kind of the curve plateaus, but, you can really not, say anything conclusively about, what emerges here. So instead, what we need to do, we need to go back to this kind of idea of toric code and think about how to measure this string operators, these string observables. But at least one type of string is actually relatively easy to understand. So let's consider the one component of the state, and that's a state which corresponds to a dimer covering. And let's draw the loop which goes around like one vertex, like shown here. So if this state is a dimer covering, then this loop will cross exactly one Rydberg atom. And so basically, if you assign to the ground state atom the value +1 and to the Rydberg atom -1, then the parity of the loop here will be -1. So this is like a Gauss law, basically. And actually, if you go now, if you take a bigger loop, then the expectation value of the Z operator will be -1 to the power of enclosed number of vertices. And indeed, if we now plot this expectation of the Z string, as we enter this phase, we observe that indeed, depending on the type of loop, we see some emergence of either positive or negative parity. And indeed, it is exactly that the number of the enclosed vortices which determines, what sort of, parity we create. So, and we observe here that we can, we have non-zero parity for, relatively large loop, for loops compared to the basically a system size, even though as the loop size increases, the parity, decreases. So basically, what these string operators allow us to do is allow us to reveal transition into the dimer phase. But there is something more that we have to do, and then we have to show basically that our state is superposition of this dimer covering. So that actually looks very scary, very non-trivial, but it turns out that there is a way to do it. And in order to do it, we need to evaluate this off-diagonal string operator. So this off-diagonal operator is an operator which acts, when it acts on one of the link of our lattice, it somehow flips, these dimers around. So the kind of the intuition for that is the following. So basically, if you look at this kind of closed string, then it turns out that this state takes any dimer covering and converts it into another one. So that's the one how it's shown here. So this, in this way, is very similar to the single qubit, where you basically have a sigma x operator, which takes your qubit in state 0 and puts it in a state 1, or it takes it in a state 1 and puts it in a state 0. So basically, the non-zero expectation of sigma x typically measures coherence between 0 and 1. In that same way, the non-zero expectation value of closed X string would really measure this kind of coherent superposition nature of the state you create. So to measure this actually turns out to be somewhat non-trivial. So you basically need to perform correlated coherent rotation of the free qubit clusters, but this is something we actually learned how to do by adjusting blockade radius. And actually with that, we can actually measure now X strings, again, over, loops of increasing size. You see that the signal decreases, but nevertheless, we see non-zero expectation value of the X string on quite sizable loops. And so this really is a signature of coherence between dimer coverings. So what is topological about all of this? And so to really reveal these topological properties, what we need to do is we need to compare closed loops versus open strings. And here, the signature of the spin liquid phase is quite dramatic. So basically, if you just take the closed, for example, Z string and compare it to the open Z string, properly kind of normalized. So in a trivial phase, they are basically identical. But once you enter the spin liquid, one of them is exact dead zero and another one is fine. Same thing with the X, it's non-zero here at the transition point, both of them, but, close to this spin liquid, open strings go to 0, closed strings stay finite. And one can actually use it to basically define an order parameter. It's actually order parameter could be open strings normalized by a square root of closed strings, and they can, distinguish trivial phases, quantum spin liquid, and other phases. And actually, from here, you can really identify the domain, where we can clearly see the onset of this quantum spin liquid phase. Just before I conclude, maybe I kind of mention that we also started kind of exploring some steps, making some steps towards topological qubit. So to create a topological qubit, you need to basically create an array with non-trivial topology, like a donut. So for example, we make a small hole in this array. And so basically it turns out that the small hole really divides all of these dimer coverings into two topological sectors. One is a sector where you have states which can be basically transformed into each other through basically local moves by just resonating a few of these kind of effective dimers into each other. But then there are other states for which in order to basically connect them from one sector to another, you have to make a loop around this hole. And even for a small hole, it actually requires a very high order process to, to really convert one state into each other. And so basically, these two topological sectors can be used to determine, two states of the topological qubit. So they're actually distinguishable by the parity of the string going from the middle hole to the boundary. Actually, it turns out that these two states are degenerate in our system, and in fact, we can prepare, in principle at least, any of the two superpositions. So in fact, to probe that you create a superposition, you have to look at the expectation value of the operator which goes around the hole. So this is the operator which X string, which connects, which would flip 0 logical to 1 logical. And so if you measure, for example, non-zero expectation value around the hole, then you basically can, find that you create a superposition of these two topological states. And in fact, this is something which we can readily do. We indeed find that, we have non-zero expectation value of the sigma x string at the point where basically all of the other properties of spin liquid are satisfied. So it's kind of a first step towards topological qubit. So I think it's kind of was maybe a little bit too detailed, but let me kind of take a step back. So this is a picture which maybe some of you have seen. So it was a very famous picture about 10, 15 years ago on the cover of Scientific American, where an artist, tried to draw this idea of this topological, qubits and how you can basically, create these anionic excitations and break them. So I think this, this artist must have thought that the physicist went nuts, I mean, how can one possibly even envision, things like this? So, and I'm sure, if he didn't think about it while he was drawing, then I'm sure if he had learned that Microsoft invested hundreds of millions of dollars in this project, he would have come to this conclusion. But actually now, using the techniques which I have just described, it turns out that we can really do these things. We can really create these excitations and braid them by just using these laser beams, in a way, and kind of moving these excitations around by just steering the system with the laser beam. It's actually very exciting. So you can now create these exotic forms of matter. You can probe them, you can, poke at them, you can study them, you can use these insights which we gain from these systems to engineer more complicated, approaches, and finally, we could use it as a platform to explore fault-tolerant quantum information processing. So I think I'm a little bit running out of time here. So let me just, maybe skip this optimization part, and so I will just directly go to the kind of, outlook. So given all of that, what are the challenges and kind of what are the opportunities? So, so what I've shown you is that, in our approach, we can basically create, these arrays of atoms and, read out these atoms individually. We can either excite them globally or we can excite them locally, atom by atom. So to really realize full potential of this technique, you need to learn how to simultaneously and rapidly excite the atoms in parallel. And this can be done, but you need to basically work on some optical elements. You basically need to create beam modulator arrays, which you can actually switch on a kind of nanoseconds scale. This is something which we are exploring. So we're also working on increasing number of atoms and circuit depth, exploring some ideas of noise resilience, in particular by controlling spontaneous emission and trapping Rydberg states, as was already asked the question. So as I already mentioned, our slowest part in this entire procedure is the atom detection. This is true both for neutral atoms and for ion traps. And actually, we have some ideas how to do it. And actually, these ideas are also related to kind of networking between these atom arrays. And this is the kind of project which we're already starting. And with that, we hope to start exploring these ideas of error detection, corrections, and kind of larger scale applications. So this is just one slide about how we are now exploring this networking idea. So basically what we do is we introduced into the vacuum chamber a very small, tiny kind of object, which is basically a photonic crystal cavity, which is suspended by on a fiber, which also allows you to kind of efficiently couple of photons in and out. And what we learned to do recently is we learned to basically, plug the atoms one by one and kind of move them into this near field of this photonic crystal cavity. And we can do it in a way which preserves atomic coherence and preserves entanglement. And I think this is actually a very exciting opportunity which for both, very fast readout, but also for scaling up, creating larger and larger atom arrays. Okay, so I think that's kind of, where this, work is going. So I hope, I gave you a little bit of a sense where this field is and, brought you to, a little bit of a frontier area of this work. And then I would like to thank, all people whose blood and sweat resulted all this work. And also, thank you for your attention.
Thank you very much, Professor Lukin, for the very, very nice talk. And I think we have time for only one more question now.
Yeah.
Yes, the question is, does the quantum spin liquid include long-range dimers, for instance, dimer with next nearest neighbor size? If yes, how can we realize it with Rydberg physics?
So in our case, we only, effectively prepare short-range dimers, right? Because dimer is basically is represented by one Rydberg atom. And of course, we can have long-range correlations between the dimers, and this is exactly what we measure using the string operators, which I described. It is possible to have different approaches, different representations of dimers, and potentially you can have also dimers on a long range, between long range, kind of spins, but this is not what we do. So what we do, we really implement something which is very close to this resonating Valley's bond stance, where dimers are short range, but there is a correlations between dimers which are long range.
Okay, all right, thank you. And Professor Lukin, if you're staying around for a while, would you mind looking through the questions from the Q&A channel? We have more questions there, so if you could answer some of them, that would be great.
That would be amazing. Actually, if somehow someone could maybe save them and email me, maybe that would be the best, actually.
Yeah, sure, I can do that.
That would be fantastic.
Copy all the questions.
Yes.
Okay.
Thank you so much, and it's great to see you.
Thank you again, Professor.
Yeah.
All right, so next we will have another talk from Professor Suzanne Yelling, who is a professor from both University of Connecticut and also Harvard University of the physics department. So the talk is about cooperative order 2D materials. Professor Yelling, welcome, if you're ready.
Yep. Hello, no, you can you actually see my screen?
Yes, yes.
Okay, excellent. I should say I'm not at UConn anymore, but thank you for the introduction.
Okay.
And thank you so much for having me. I have to say, a visit to Purdue is always a particular question, a particular pleasure, and it's great that you have me. And of course, the fact that it's virtual is a little minor glitch here. So today I will be talking to you about a topic that is close to my heart, very quantum, and at the bottom of quite a bit of quantum information applications. It is not, however, kind of geared towards quantum information. In that sense, it probably differs a little bit from what everybody else is talking about. But I will mention, at least at some places, how that can be worked. So before I start, please do ask questions. My talk is modular, so I can just cut out modules and can answer questions as long as this is wanted or needed. I will try to keep an eye on the participants, but it's a little bit much to handle. So if anybody has a question, perhaps you can just yell it in, that would make it easier. Okay, so let me first start with telling you a couple of the goals that we have with this kind of work. So at the end, I will be talking about 2D arrays, something like what you see on the screen right now. These goals could be any quantum radiators, but for simplicity, just imagine they are two-level atoms, and I will also be talking about atoms. And I will show you later how one can potentially use other materials, but for simplicity, just two-level atoms. Then the question is, how can one use an array like that to reflect light in a quantum manner and with very high efficiency? Then the second module I will show you is how can we use this for spatial light modulation to, for example, write something interesting. Then I will go into the age-old question, how can we make the effectiveness of the interaction of a single photon with a single atom or a single radiator better? And here I just want to remind you of the size of an atom, which I will do when I get to this. And the question is, how can we use the array to make the effective size a lot bigger, and use this potentially, for example, for quantum gates. And then perhaps even kind of build an on-array quantum network. The next application will be, how can we do photonic edge states? And that goes a little bit into the topology questions that Misha has just talked about. And finally, I would like to briefly tell you how we can create a quantum mirror, such that both the original and the reflected image are entangled, well, first superposition and then entangled, and how that potentially also can be used for quantum information science. So let me get started. So the first part of the lecture kind of roughly consists of two parts. The first is an explanation of the particular type of non-equilibrium interacting systems that is at the bottom of everything I'm going to talk about. And I will talk a little bit about the physics really on the microscopic levels, because in the applications, I will not be talking about that anymore. And the second part, which is probably the longer part, I will just show you the number of applications that I've just mentioned. So let's start with the questions, why cooperative effects, and why do we even bother? Okay, so the why do we even bother comes actually perhaps a little bit more only at the application side. So first I will explain what they actually are. So this cooperative effects is a little bit of a fancy name for what Robert Dicke started like over 60 years ago, who discovered what is mainly called nowadays superradiance. And here is a quote from his paper, 1954 paper. Let me see whether I can actually kind of get the laser pointer. No, I cannot. Can you? So what he does, he says, for want of a better term, a gas which is radiating strongly because of coherence will be called superradiance. And he did that apparently with a little bit embarrassment, but the name has stuck. And please do note that coherence is really the important word here. Below here is a copy of the paper that he did. So this is basically what we will build this on. But for that, I would like to take a huge step back. Namely, briefly, what do I mean when I talk about an atom? So the atom, as you all know, has different orbits, or the electrons have different orbits with different energies, and these different energies or these orbits or states we call levels. And these levels, they have also sublevels, like, for example, hyperfine, Zeeman states, etc. And what we do in what follows is that we pick and choose just the ones that we need of those. Most of the time that will be two. Like for example, let's say here this one and the sublevel of this one. Sometimes it will be three, and I will mention that when we need three. But if I talk about atoms, I really talk about these kind of picked and chosen sublevel combinations. The next question is, because that is again at the total center, is how does it couple to light? So here we have the two levels with an energy of the upper level, an energy of the lower level. And we have a photon which has the energy h nu. And what we want is that the photon or the light field has the same energy as the difference between these two atomic states. And if that is the case, then we can start with the atom in the lower state. and a photon, which then gets absorbed in order to lift the atom into the excited state, which we generally call excitation. And of course, then ideally this goes back and forth, right? And with that, I will start with the cooperative effects. Please, again, interrupt me if there are questions. I think so far this is still kind of probably a review for most of listeners. So let's start with a single atom. A single atom in the excited state is subject to spontaneous decay. So spontaneous decay means the atom goes into the lower state and emits a photon. This photon, if we measure its intensity, gets an intensity probability, or if you do that often, an average over time, which goes down exponentially over time. So this is single atom physics. Now we look at two atoms, but the two atoms are relatively far away. And if we do the same thing, we let them decay. They, of course, not necessarily decay at the same time, and let them radiate. We get still exactly the same intensity per atom profile that we had before. So now what happens if we put the two atoms very close to each other? And very close means very close to compared to the wavelengths of this transition frequency. If we let those decay and look at the photons, you can already see that the photons are now close enough that there might be some coherence between the two. And this coherence leads to the fact that our intensity per atom profile now changes a little bit. And this is what the cooperative effect is really all about. So of course, this is getting much more interesting if we have many close atoms. All of them, please do note, start in the excited state, decay, and emit. And please, here you already see, first of all, what ideally one gets is a coherent superposition of all of these photons. And because the atoms are so close together, their decay really happens in a coherent fashion, which is somewhat similar to stimulated emission, like in a laser or so. And in this case, the intensity per atom has a completely different profile. As you can see, it actually rises initially before falling off. And this is because there is a short time where we get this strong kind of superposition between these atoms. Like we have, strong superposition between the photons. And you know that if you add up the amplitude of n photons, the intensity goes like n squared. So this is why superradiance is an n squared effect. Okay, so this is where this very, very strong peak comes from. And this is really what is at the essence of pretty much any superradiance paper or research or whatever you would talk about. Mostly people also speak at the same time, not only about the photons, also about the atoms, and call this a build-up of collective dipoles. This is this kind of stimulated emission-like type. Please do note that this collective dipoles is put in quotes because it's a little bit of a misnomer, but I'm not going into detail of that for right now. All right. So there is thus two important aspects to cooperative effects. The one is the collective effects, where you just have many particles which are close enough together to act coherent. And that has basically two aspects to it. The one is that it's collective, many particles. One aspect that they have not mentioned is also that if you send a photon and want it to interact with atoms, obviously it has a much higher chance to interact at all if there's a lot of atoms than if there's only one. That's also typically kind of called a superradiant effect, or often is. The second aspect, which I have not spoken about, is that the atoms actually have an effective interaction with each other. So they kind of exchange photons, both real and virtual photons, and this is what amounts to the dipole-dipole interaction, and that's what we go into now, and also mostly later in the talk. So what that means, the fact that there's this exchange means that if I talk cooperative, that's actually more than just collective. Collective is just the first part. There's just many particles. Cooperative also immediately means that there is some interaction between the particle that does something to the physics. And what it does, that's what comes now, okay? So the very simplest form of the exchange interaction is what we do with this example. And this is the superradiance, which I just talked about. So this one, I like to kind of put that in a little bit more kind of populistic picture. So what is the super part? It is not just this kind of good guy, Clark, who kind of is so great that it's really like you have a couple of them. But this strengthening of his powers actually results into something very different, namely Superman. Of course, I don't like Superman so much. I like Superwoman a lot better. But that's basically how you should imagine superradiance or cooperative effects. So before I go and show you this in a somewhat more microscopic picture, I would like to briefly give you an outline of this lecture. So first I will go on with my explanation of cooperative effects, and then I will show you a couple of applications. And now let me start with that. So the easiest example, obviously, of having more than one atom which kind of interacts is two atoms. And that's exactly what we have here. So what I have on the screen here is the level scheme of two level atoms with which are distinguishable. So the four levels are GG, which is both atoms in the ground state, EE, which means both atoms in the excited state, EG, which is first atom in the excited state, second atom in the ground state, and then GE, which is the opposite. Okay, so this is basically my first two atom picture where the atoms are far enough apart that they are distinguishable. So now what happens if they are indistinguishable? Then we cannot distinguish the GE from the EG anymore. And in such a case, the eigenstate of the system instead are the symmetric and anti-symmetric superposition of the partially excited system. And so what happens if we now put an electron into this, or a couple of electrons into this upper level, where we have two excitations? What it does, it will decay only via this pathway, via the symmetric state, or so-called Dicke states, because the other two states are both forbidden, and both basically the two pathways from EE into EG and EE into GE destructively interfere on this pathway. So what happens is that basically two possible pathways, namely along this side and along this side, all condense into one, and therefore we get a stronger effect of this decay. This is what we saw in this picture before. So as please to note before I go on, I have this orange names here. This is if you go into an angular momentum picture where you say J equals 1 and the triplet state, which is the Dicke case or triplet state, and J equals 0, M equals 0 for the singlet state, just for those people who want to see how to read these states. What I showed so far is basically, is the case if there is no interaction. In this case, the symmetric and the anti-symmetric state are exactly the same, are exactly degenerate. But now we have, in addition, this dipole-dipole interaction. And what happens with this dipole-dipole interaction is that splits the symmetric from the anti-symmetric state. And and can therefore be distinguished, and at the end results in all of the, and results not in a very trivial manner, I should say. There's a couple of steps in between in all of these so-called cooperative effects. So it's really both the indistinguishability and the fact that they are interacting with each other that makes something cooperative. Just in order to repeat myself often enough that this is clear. So this, there are two things that I also want to add to that. The one is that this exchange interaction in the system like this is usually dipole-dipole mediated. So when I talk about interaction, I talk about dipole-dipole interaction. It doesn't have to be though, but this is kind of all the numbers and curves, etc., that I show are based on dipole-dipole interaction. The second is that this interaction does not only create a shift, that's the one that I showed here with this arrow, but also a broadening or a dissipative part, which is basically exactly a Kramers-Kronig relation that you know from reflection as from linear physics, only that this is a Kramers-Kronig relation that is really based on this nonlinear physics that one sees here with interacting atoms. And we will see this kind of shift and broadening relationship soon again. Okay, so what is superradiance or cooperative effects? And here, this is basically similar to what I said before, just a little bit different words. So first of all, it's everything that involves Dicke states. So Dicke states are these fully symmetric states. And everything that has basically collective effects, which usually go with square root of n, physical, a typical kind of physical system is a bad cavity limit of a laser. Most people would call that superradiance. But there is also the fact that only those systems are called superradiant that involve cooperative and nonlinear effect. For example, this exchange interaction that I want to tell you. So there is a little bit of a difference of opinions of what exactly constitutes superradiance. I'm of course of the opinion that it has to involve both both number one and number two here. And that's what I also assume for the rest of the talk. And so superradiance, and I should have said that earlier, superradiance is actually the cooperative effect that goes with decaying atoms and the light emission. Cooperative effect is the whole field where you have systems like this. This is all very hard to calculate, and I'm not going into detail, so I will go over this slide just in order to get through and in order to prove that we have actually done it. But here I show you just one example of what comes out. So this dotted line is just normal spontaneous emission. It's basically the same line that I showed you in this introductory slides. But then there's the blue and the red solid line. And the blue solid line would be just the coherence effect without the exchange or without the interaction, whereas the red gives and that's again this intensity over time kind of picture that we saw before. Only if we actually have this exchange interaction do we get true superradiance where we get this increase in intensity over time. Okay, so that was my very, very brief run through of what cooperative effects are. And we will not go back to superradiance, and I will not give any microscopic explanations of the interactions anymore. So now would be a good time to ask questions if you have questions about this part.
Professor Jelena, I don't see questions for now.
Okay,
so,
very good,
yeah.
Excellent. So then let's go on and let's have a look at application, and all of the applications that I will show will be what we call atomically thin mirrors for want of a different words. It's not, the mirror function is not always used, but it's always the same system. So the system is, as I showed you before, just an ordered 2D array of atoms. And what we want to do quantum optics with these atomically thin materials. And the goals of that is that we have a very strong optical response, and that this optical response actually can be engineered. And in particular, which at the end will be very important, is that guided modes inside this material can be constructed. And so at the end, what we have is what one could call, what one could call an atomic matter surface. So let me briefly tell you how this works. So let me just give you an idea, the idea and setup. And here we are looking on the array of atoms from the top. So the first thing is have a little bit of a look at the length scales. So I have put, as I put before, again, the cross sections of the atoms in here. These are these little circles around the atoms, just to indicate that the lattice constant here is supposed to be roughly of the order of the wavelengths. There are interesting things that happens if the lattice constant is much bigger, but the exchange interaction or the cooperativity will not happen. There are also very interesting things where this is where the lattice constant is orders of magnitude smaller than the wavelengths, but the particular kind of effects that I will show you will need them of the order of magnitude, similar order of magnitude. So the question is this a system where we can get complete reflection from? This is a very natural question, because if you look at all these cross sections that I did there, it looks like the atoms about tile the surface here. So we could think there is a complete reflection, and we can make some kind of educated guesses of what exactly the relationship between the wavelengths and the lattice constant should be. But it turns out, if one calculates that it's not quite what we would guess, and that it happens exactly at two values. Namely, this system acts like a perfect mirror if the lattice constant is exactly 0.2 or exactly 0.8 times the wavelengths of the transition. I will explain you in a second where this comes from and how this looks like if we change our lattice a little bit. But here is a nice picture that my postdoc made to show this. Please do note here we have not perfect reflection. There's still a little bit of light going through, but it looks prettier this way. So, and again, a reminder, we do need these cooperative resonances in this situation. Nothing of what I will tell you works if we don't have the cooperativity. So first of all, I would like to give you a little bit of math, and this is very, very, very simple math that explains you why this perfect reflection happens. And this can be done via input-output theory. So we are looking at the field that comes out on either side of our surface. Please assume, and we just assume plane waves here, an infinitely large lattice, the simplest case that you can imagine. So what we get as an outcoming field is the incoming field, which propagates in plus z direction. So it's e to the ikz times z, plus the scattered field, which is given by the second term with the scattering constant s. And if you look at what we want is reflection. So that means that if we find for some reason a scattering constant that is -1, then you see that the forward direction, the one where z is larger than 0, exactly cancels. So perfect reflection comes exactly if our scattering constant is -1. So that means it's an easy problem. We just calculate the scattering constant, right? And this turns out to be exactly the following expression. And as you can see, it's basically like a normal Lorentzian, like what we, for example, would get from a 1D waveguide with a 1D radiator perfectly scattered, coupled. where we have the gamma divided by the delta plus 1/2 times I times gamma, only that the gamma now has a gamma plus a collective gamma, and the delta has a delta plus a collective delta. And here these collective terms are exactly come from the dipolar interaction between all the atoms, and are exactly these two Kramers-Kronig terms, namely the delta is the shift and the gamma is the broadening. And these are basically just found, this is a complex number that's found by adding up all the possible interactions that you have between any two atoms on this lattice. So it's conceptually very simple to do, numerically a little bit harder depending on how your situation is. But if we now look at the form of S, then we see that we get this desired for S equal to -1 exactly when the total detuning part, namely the outside detuning, namely the detuning between the light and the incoming light and the atoms, plus this collective detuning exactly add up to 0. Okay, so that is where our perfect reflection happens. And so the simple thing is to just plot the function of this collective delta as a function of lattice constant over lambda. And we see that this crosses 0 exactly twice. And so this is the case where the outside detuning, this is what I showed as small delta, is exactly 0. And you can see that this happens, these two crossing points happen exactly at 0.8 and at 0.2, which is exactly where we get our perfect reflection, which is this yellow curve here, which just shows the reflection coefficient. And of course, we can now look at a couple of other detunings and see that we can get actually perfect mirror pretty much anywhere between A over lambda equals to 0 to A over lambda equals to 1. And so this is actually a very flexible way to make this atomic mirror. With this kind of relatively simple explanation, let's go just one step further. First of all, I would show, we have done this calculation so far just for a square lattice. Not very surprising. If you have any other ordered lattice like triangular, Kagome, or hexagonal lattice, we get qualitatively the same results. It's just that the 0.2 and 0.8 go to a somewhat different numerical value. So there is, however, so this is this question of the reflection. There is one more aspect of this cooperative 2D array that is interesting and useful for applications. And that is if we look into the band structure of that. So the band structure of this is a very simple one. The inset on the right side gives the gamma X and M symmetry points, and which are then plotted on the x-axis of the system. And we have the three directions in red, yellow, and blue, and the circular polarized in purple. Why is this interesting? This is interesting because we have two very distinct areas in that. The one which is close around the gamma point is within the so-called light cone. That means that the K value of the excitation on the 2D lattice is smaller or at the borders equal to the K value of the light in vacuum. So that means in that case, the excitation on lattice can very easily couple to the vacuum excitation. So if we have an excitation of that type, it will just radiate off in free space. On the other hand, if we are outside the light cone, that means that the K value is too big, and if it would radiate off into free space, energy would not be conserved. So what happens is that therefore, if we ever manage to get an excitation on the lattice somewhere outside of this light cone, this excitation basically will live on this surface forever, which makes the system, in addition to a mirror for light that comes in, also a very, very good waveguide in the case of these excitations that are outside the light cone. And for the applications that I will show you, we will combine this reflection and this waveguiding properties in order to manipulate our surface. Okay, any questions? Okay, so let's go, let's look a little bit at the possible implementations that we can get in this case. So the first example is obviously atoms in an optical lattice. From what I showed, that is not very surprisingly the very most kind of straightforward way. And one example would be the quantum gas microscope that was developed by Markus Greiner, and in the meantime is done all over the world. It turns out that this is a very good system because it has basically all the right properties. But of course, it's a little bit difficult system to deal with. You need to build a quantum gas microscope, which is a major effort. So it would be nice if one also would have some way to make such a system in an easier way. And one other way are solid state 2D semiconductors, and in particular, these so-called transition metal dichalcogenides, or TMDs or TMDCs, which, if you look at the picture that Wikipedia shows from them, basically from the top look like a graphene lattice. So they are just really nice honeycomb lattices. But from the side, we see that the two ingredients, namely the transition metal like molybdenum or tungsten, make only half of the lattice, and the other half is made by these dichalcogenides like sulfur selenide, which kind of double up in the kind of short direction, such that from the top they, as I say, look like graphene and act to a large degree like graphene, but have one enormous difference. And this difference is that graphene cannot hold any excitons. So, and I don't want to go into what excitons are, but excitons are basically, if you excite any of the individual electrons in the system, they act a little bit like atoms. And they, of course, have major differences, but you can imagine then to have a similar structure to atoms. And whether they exist or whether they are stable, and in particular, whether they have good selection rules, is determined by the material. And it turns out that this is excellent in these TMDs. So because they are such great materials for excitons, there are actually a lot of experiments on those, and some of them are done also at Harvard by Hong Kong Park and Philip Kin. And they have actually done this mirror experiment with molybdenum selenide, and here are two pictures of that. So this is on an HBN surface, and if you look at the left picture, there somebody drew in where the piece of molybdenum selenide is, because you would not see it. You see the HBN, which is the kind of surface on which you grow this. You see the platinum leads, but you don't need this particular system. On the right side, however, you shine in light of exactly the right wavelength, such that it hits this mirror resonance that I was before showing you. And in this case, you see that this piece of molybdenum selenide here is nearly as bright a mirror as the platinum leads. And this is a little bit slightly different from the situation that I showed you. Here is they also have drawn a spectrum of that. And I don't want to go deeper into this, but the point is, in principle, this is an excellent system to do these kind of experiments. And when I now go back to various type of applications, part of them are kind of with atom in mind, and part of them are with TMDs in mind. And the next application, the spatial light modulation, is actually on TMDs, and is in fact, the experiment exists. And let me just briefly tell you about this. So the idea about so what one wants to do, one wants to do spatial light modulation, ideally in a quantum level of single photons, etc. But the thing here is that it's done on a nanosecond scale. So usually when you do light modulation, you need to kind of change your geometry, etc., and all of that takes time. I think Misha, in a very different context, has talked a little bit about that. Here, the goal is to do that very, very fast. So what is our systems? Here is again our scatterers, and these scatterers here are shown from the side. So they are into the screen, they are long. And then one sends a little bit of light in there. And this light gets reflected. And this reflection, you can see, has, like this kind of typical Bragg scattering, has constructive interference in some directions and destructive interference in other directions. And where you will actually see the reflection are in the constructive directions, right? And I have already kind of drawn them such that you basically see the constructive direction. So now what happens, what happens if you now take a part of the atoms, and I made them now a little bit darker, and change them. And I will show you in a second how you change them. You change them such that the reflection gets a different phase. So this little bit darker blue has a different phase. So now when the phase changes, this constructive interference happens in a different direction than it did before. And that's the whole idea of this spatial light modulation. So this was my not very artistic rendering of that. So this is how the system actually really looks like. And for this one uses a TMD. The TMD is in the middle of the picture. And it's sandwiched between the HBN. But importantly, it has two leads. The top lead, which is this gray one on the top, goes over the whole extent of the material. The bottom lead is basically creating this kind of dark red atoms that I had on the previous picture, and goes only over half of the distance. And thus we have this disparity of the atoms, or it's not atoms, it's excitons in this case, which create these interference patterns, which is here shown in this on the top with these different kind of outgoing waves. And we see that there's a certain direction where we have constructive interference. So that's basically the whole picture. And so the question is, first, this is how the material looks like from the top. And what you can do now, so you have this line where the lead, up to where the lead goes. And now we can change the direction that the light takes perpendicular to this line. The way how this ideally looks like is at the end, like in this picture. So this is an artistic rendering already of a situation where you don't have just one line, but here the inset in particular shows you how to change the phase of these, or how to change the phase of the reflected light. That is just done by changing the energy of the upper level of the excitons. And this is, of course, this is very exaggerated here, but changing of the energy changes the phase of the reflected light, and this combination leads to the fact that we can have the spatial light modulation, and at the end, of course, ideally create some pretty pictures with this. Here is already a 2D picture is shown, and I showed you only how to do that in 1D so far. So here is how to do it in 2D. So it's basically there are two, as you can see, there are bilayers, single monolayers, dual gated, single gated, so that you have just 3 different results. And here there are these 3 different regions marked with these kind of outcoming photons. And if you can steer the voltage of the 3 different regions, you can actually steer your beams in 2 different directions. And if you do this, then you can create arbitrary pictures in 2 directions. And this is this picture that I showed you in the beginning. And please do note that these are actually a steering range that is rather macroscopic. So this is the y direction and the x direction in actually degrees. So it's not huge, but you can actually measure it. So I should also say this is so far actually not really a quantum effect. This is a fairly strong light beam. And this is also mostly done via Bragg scattering. But of course, because of all of these quantum properties that this system has, the kind of quantum effect is the next step from here. All right, let me make a brief break before I go to the next and ask whether there are some questions regarding this.
Yeah, I don't see any yet.
Yep. Okay, fine. I did just, you can also just yell in. I'm not going to always wait forever, but so the next is, so now I really want to go to single photons and single particles. So here, and I give you only the very rough idea here without going into all the math, which kind of gets already a little bit. I should also say the previous one was an experiment. This is so far only a theoretical proposal. So here we have a single atom, which we ideally want to kind of interact with a single photon in free space, which is hard. The cross-section is only a lambda squared, as I said, and the photon can be anywhere in space. So if you send the photon in there, the likelihood of them to interact is very small, and we don't want that. We want it deterministic, right? So what we do is we put the single atom as an impurity in such an array and hope that we can get the cross-section as big as the array. So you can thus imagine the array as a kind of a fishing net or antenna array, but in a quantum matter, there are actually major differences to an antenna array, but intuitively that makes a lot of sense to actually catch all the light and all concentrate it on the single impurity atom that we have in the middle. And so the question is, how well does this work? So we have a couple of pictures where we just looked at what happens if we have only an impurity in free space and normalize the scale that we have here to exactly the scattering of a single atom in free space. We get a factor, the highest factor is 2 because we have an interference between because of near field effects. And so this 1 and 2 here set the scale of the scattering strength. Now we look at the same thing where we have the atom array in the, not quite at the reflection, but very close to the reflection parameter. And here we see the scale actually goes up to 4 compared to the previous one, which is because we have constructive interference on the really bright spot. And now the question is, what happens if we put the two together? What comes out is a picture roughly like that. And here I would like to emphasize that this is on a very different scale. And we plotted this only up to 100, but it turns out that very close to the atom, it's to the impurity, it's actually considerably higher than that. And I don't want to go into the calculation, but I would like to kind of tell you one more detail. Namely, you remember when I showed you this band structure before, where I said where in principle, the atoms are not allowed to interact with the environment. Now, if you go even a little bit further out, these excitations cannot be held at all. So what you do, you detune the impurity a little bit from the array and make sure to send in exactly the right photon frequency. And there is this region where the array can guide the photon, but cannot hold it. So there are only virtual excitations on the array. And because the excitation has nowhere else to go, it all goes on the impurity. So we really truly have a kind of a fishing net for a single atom, for a single photon. And of course, what we want to do here is we want to ideally kind of have two impurities or two qubits being able to interact. And so we put both of them on there and look at how well they talk to each other now. Given the fact that the array doesn't hold excitations, but the impurities do, the expectation is that we would have just an interaction either on the one impurity or on the other, or some kind of exchange between the two. And this, as it turns out, actually exactly happens. So first, I would like to briefly quantify this a little bit. So how good is this coupling between the impurities? And this is kind of drawn as compared to the decay into free space. So one example would be that, where we just look at the two impurities, impurity 1 in blue and impurity 2 in orange, and let's just run it. So the question, how far does that go, is basically an effective kind of an effective interaction strength between the two, and you see they decay. The quality of that decays, but relatively slowly. And what is the quality factor of this? So we are basically on this narrow yellow kind of line in the parameter space. Please do note, for some reason, I cut off the x-axis. I show you in a second. So this is the tuning versus the decay ratios. And here we can see that we get a quality factor, which is about up to 10 to the 2. And there are other regions in the parameter space where exactly the opposite happens, when there's basically no coupling and everything goes off. And here is a little bit a different place in the parameter space. Sorry, I told you something wrong. On the x-axis is actually this A over lambda region. And as you can see, this kind of fully reflective kind of region turns out to be somehow close to where we want to be. Please do note that in the second example, we have changed something else, which I don't want to go into. But here, the quality factor actually goes to 10 to the 6, or even better. So we can really kind of fully have these two impurities interact with each other without losing anything. I would like to say that we actually did a couple of more things for that. So we, first of all, there is, if we have a single atom, this is in principle a perfect nonlinearity because it's an atom and not a harmonic oscillator. In order to prove that, one has to find the transmission G2 function, which we haven't done yet, but this is in the works. And then, of course, the idea is that we use this kind of interacting two or many qubits on array in order to make somehow ideally networks of those, and also make gates. And in order to make gates, one needs to kind of access more than just two levels. One needs to access at least 3. But we have some work which is so far not published yet, which also shows that you can do kind of CNOT gates and stuff like that between those levels. So, and I see I have with questions only 10 minutes left. The next part would be the topology. And if you have questions regarding that, I will show that. Otherwise, I will just jump directly to the last topic, which is the quantum matter surface, especially given that Misha has talked already so much about topology. So the quantum matter surfaces basically now goes back to atoms and starts again with basically exactly the same idea. I should say, again, this is just a theoretical proposal. As you can see, it's a little bit more quantum than everything else. So that's probably of all what I showed you so far the hardest to do. So what happens if we have now a superposition of such a state with a state where all our atoms are actually excited? And ideally, our superposition state is actually a cat state, or not ideally, but as an example. So either all of the atoms are in the ground state or all of the atoms are in an excited state. So we have a cat state of this whole array. So there are, of course, now two questions. First of all, how can I create something like that? And I will show you that in a minute. And the second question is, what happens if we have that and shine sunlight in? And that's the question which I first will answer. So let's assume we have this quantum reflection, so this 0.2 or 0.8 that I showed you before. In this case, if our array is in the ground state, we get exactly this reflection, which we call flip up. Alternatively, we can have this in the excited state, in which case this mirror thing does not happen and the light just goes through. Please do note that compared to a real mirror, like the silver mirror that we all have in our bathroom, these arrays are extremely dilute. So unless you work hard, everything will go through. And this is exactly the situation that we have here. So this is if the flip is down. But now if we have the superposition of the two, we actually really have a superposition of reflection and transmission. And so what we effectively get, we get a superposition of atomic responses and entanglement of the state of the atoms with the state of the field, namely whether it gets reflected or transmitted. And this is basically what I was hinting at when I showed you this picture in the introduction. We cannot quite do apples yet, but hopefully we can do something more useful. And so the question is, how do we get these superposition arrays? So for that we need two more ideas. One of which Misha has talked about, that are Rydberg states. And Rydberg states are very interesting because they have a very, very strong interaction over a very large distance. So I'm not going into detail about that. The second is EIT, or electromagnetically induced transparency. And what that is that you have, if you have a 3-level system, for example, like this 3-level system that we have on the side, if the two end states, which would be the ground and the Rydberg state in this case, are coupled by two fields via the middle state, which is the normal excited state, the middle state basically suddenly becomes invisible or transparent, the transition to that becomes transparent if we have two photon resonance of two fields with G and R. Okay. So in this case, in this first picture, that is exactly the case. So this transition G to E is invisible for the light. Invisible means mirror doesn't work, light goes through, right? So the other case is if we have, and here the picture is not, it's not quite accurate. So we have a Rydberg state that is up here. And our fields now are not quite, actually, no, the Rydberg state is here, but the eigenstate of the system is up here because there is very, very strong interaction between a Rydberg state and another Rydberg state. And this very strong interaction kind of effectively lifts the state. So our 3 states would now be this upper state and the single excited state and the ground state. And of course, now our 2 fields are not in 2 photon resonance with that anymore. And therefore, this transition suddenly becomes visible. If this transition is visible, we are in the mirror situation and we get this thing reflected. So why is that a nice situation? Because even one single Rydberg atom in this situation is enough to switch us between the left transparent and the right reflective situation for all the other atoms, right? So that means that what we need is not a superposition of many atoms, but we start with a superposition of only this one atom. So we basically, our cat state originates from one kind of superposition of a Rydberg in a ground and a Rydberg state. And this basically gives this whole picture of a quantum atomic response. And as a very last picture, I would like to show that this now can be used for, in a very simple manner, for quantum information science, and in this particular case, for example, for quantum error corrections. So here, these green lights are the beams. The beam that goes through, we call 0 qubit. The beam that gets reflected, we call 1 qubit. And instead of having this whole array act together, we use as a single kind of qubit, effective qubit, we just use small areas of the arrays. And because we now can access them all in parallel, we have massive redundancy in the system and have therefore an automatic error correction, even if we send in only a single photon. And this goes down to what is called pre-cluster state, quantum light modulation for single photons. And I'm not going into any details of that because my time is up. I do have an outlook, which is also not so important right now because I really want to show collaborators. The 5 people at the top are the people who did the most work. Effie was my postdoc. He's a professor at Weizmann right now. He kind of invented all of this 2D material stuff with this mirror, etc. Taylor Petty is my student. She did the single atom, single photon. Janosch did the topological. He graduated from Mischa's group and has now his own company. Trond did the spatial light modulation. He is still a student in Mischa's group. And Rivka was a postdoc here, or is actually still a postdoc here, but is on her way to take a position in Jerusalem. So, and the left is all my group, who also contributed somewhat, but not as much. Other students and postdoc and PIs. And then I, of course, want to thank my money givers. And finally, I want to thank all of you for listening.
Thank you very much, Professor Yelin, for the very, very interesting talk. And for the audience, if you have any questions, you can just feel free to unmute yourself and speak up. So while we're waiting, I do have a question regarding like the reflector work you mentioned. Mm-hmm. So basically, based on my understanding, for the perfect reflection, you will require like the lattice, the atom spacing, something like near the wavelength.
Yep.
Right. But you also showed in another work that for the people have done it with TMDCs.
Yes.
So how does that work?
That's exactly, you exactly put your finger on that. And this is why the TMDC work is not perfect. So obviously the lattice constant in the TMDC is a priori the lattice constant of the semiconductor, which is kind of course of the nanometer range, right? Mm-hmm. While the light is still somehow close to visible. So this gives us quite a couple of orders of magnitude difference, like 5 or so. So one of the ways, and you still get the mirror, but the mirror is now resonance width is now given by the native exciton wavelengths, and it's not quite as manipulable as it would be if you would have the correct distances. So people have been thinking of how to change these distances, and there are various ways to do it. The most promising and what people are trying to do right now is to use the so-called Moiré patterns, double lattices. And these Moiré patterns, if you take 2 of these lattices and overlay them with a very small angle between them, gives a lattice that has an effective lattice constant that grows much bigger as you make the angle smaller. And The hope is that the effective lattice constant kind of takes this Moiré lattice constant, but this is difficult and nobody has really quite proven that this is possible yet. So there are a couple of things that you can do with these TMDCs already and a couple of things that hopefully kind of will work. But yes, that's a work in progress.
I see. Thank you. And like among all the like quantum optics applications you mentioned, which one do you think is like the will have the most exciting near-term applications, like realization in terms of like practical realization?
So I did not talk about all of them, and I really, I mean, you asked me about near term. So most exciting and near term is not. I think the quantum matter surfaces is probably most exciting. The most near term, however, is one that I didn't even show you. The nice thing is that this is a mirror which has its own degrees of freedom, namely whether it's actually a mirror or not. And it's also extremely, extremely, extremely light. And so a very interesting application of that would be quantum optodynamics, optomechanics. And namely when you have a quantum interaction between in a cavity with either one or two of those atomic mirrors. And it turns out that these are not that hard to make and I mean, from the numbers of how far you can get down with cooling or how well you can actually couple the light to the modes of the mirror, the numbers that you get there is extremely, extremely promising. And I should say the reason why I didn't include that is that Effie, who is now at Weizmann, I mean, that's right now basically his main, or one among his main topics, and he has written a number of papers of that. And so he is really the owner of that. But I think that one should be actually pretty easy to realize. And you can really go down to quantum level with that.
I see. And all right, so let me check. We do have a question from the chat. So the question is, how quick is the transition between the reflection and non-reflection state?
So if one uses this setup in this last example that I showed, that's basically just the time that it takes you to excite a Rydberg state. And the time it takes, this is usually done using stirrup, and I'm not going into stirrup. It depends on the particular atom, but it's of the order of magnitude and probably a little bit faster than the typical decay time of an atom. So, which kind of would put it somewhere between the nano and microsecond range.
I see.
And actually, I should also say that what I showed in the beginning, this kind of fast light modulation, is basically, I mean, that's limited by a somewhat similar time scale. So whatever time scale you can do with the one, you probably can do with the other.
Okay, great. Thank you, Professor. I don't see other questions. Yeah, but I'll be happy to follow other questions from the audience if they have. Yes. After this.
Again, if you email me questions in case you're interested, I will be happy to answer them.
Yes, thanks very much,
All
Professor.
right, thank you so much.
Okay, and all right, thank you again for all the attendees and the audience. So we are done with the afternoon session here. We'll have a break, and please consider attending the science communication workshop after this. It starts around 3 p.m. And thank you all for attending, and have a nice afternoon.
David. Let's make in the preparation for the workshop, Zorin, Neil, Pratik, and Zach co-hosts so that they can share their video and screens.
Hey, Alex, what's up?
Hello, Zorin. Thank you for joining. We will start in about 8 minutes.
Okay. Neil, are you there?
Hey, Soren, hi, how are you? You guys hear me okay?
Pretty good. Yeah.
All right, Soren, I sent
Yeah,
over
do you
that
have
little...
Did I have
Sorry, what?
I said, do you have the before and after versions of the slideshows, or does Alex have them, or should I bring them up somewhere? Or will they have it?
I have our speakers will have it. Just a reminder, we are live already. So I think some of the attendees still with us, but we will start the session in 7 minutes.
Okay, okay. Well, we'll keep it. Okay, don't worry. I'll disconnect and reconnect really quick. I'm moving to a computer.
Hello again.
Hello, Zoran.
Hey, Zoran.
All right, it's 3 p.m. and we can slowly begin our next session. Hello, everyone. Welcome to the second half of today's program. My name is Alexander Senichev. I'm postdoc at Purdue University, and I will moderate our next event. I'm very happy to introduce our very special event called Engaged Science Communication Workshop that will be provided by Zoran Adamatei, who is a professor of communication and associate dean of research and graduate education in the College of Liberal Arts at Purdue University. And also Dr. Neil Dilley, who is a research scientist in Berkman Technology Center at Purdue University. In this workshop, they will present an innovative approach to science communication, which focuses on violation expectations and learning. And the theory of the presented approach of the storytelling is derived from information theory and the psychology of novelty. If you have any questions to our speakers, please feel free to type them in the Q&A chat and also on YouTube chat. So welcome everyone. And with this, I hand it over to our speakers.
All right. Thank you very much, Alex. Thank you very much, everybody, for making time to come join us at our conversation about engaged science communication. Engaged science communication, I want to emphasize. It's not just about science communication. There are many ways to do science communication, and many possible ways. We want to focus on engagement. So the big question that we have for you today is, for us, the big question that I'm trying to answer with you today is, what is engaged science communication? By the way, I'm Zoran Adamatei. Alex just introduced me. I'm a prof here at Purdue University. I've been teaching for many years in the School of Communication. More recently, became an associate dean of research. And in this capacity, I started collaborating with Berk Nanotechnology Center, with Ali Shakuri, and with Neil Dilley, my partner in crime, trying to rethink how we train our graduate students to tell the story of their research in such a way that they get they get the best job they can get. So what you'll hear from us today has to do not only with making people better, or making scientists better communicators, but making them better communicators with a purpose, which is to engage an audience, to attract attention, and to get noticed in a variety of contexts, not just at conferences. Actually, conferences are the least of our concern here. Our concern here is to train our students to be able to communicate to non-scientists or to people who are in leadership position in scientific organizations who know nothing about your scientific domain. These thoughts are just a brief introduction to what we're going to talk about and how we're going to do it. But before we get in a little bit deeper into the conversation, I would like to allow, again, my collaborator, Neil Dilly, to say a few words from a scene from his perspective about our collaboration, the goal of what we're trying to do, and all that. And then we'll switch to the topic of the day, which is how to do engaged science communication. Neil?
All right. Thanks, Soren. Hi, everyone. I'm Neil. I'm a research scientist here at Berkeley for about 5 years now, and I've had the pleasure of getting involved in the Shark Tank science communication. And the second go around, Soren and Ali Shakuri did the first, and I came on board during the second time. And as somebody with a background in physics, studying arcane things, I really have learned to appreciate over the years the importance of rising above the process, the details of the process, and identifying the why and the connection, and realizing slowly, and I'm kind of the initial one of the guinea pigs here. What we're talking about is storytelling always, and the assumption is that our audience will always be engaged and will always be interested, because who is our audience? They were our instructors when we were undergraduates. They're our advisors when we're graduate students, our lab mates. And gradually we graduate from that, and we need to go into a world where we need to convey the importance of what we're talking about, whether it be science or more generally scientific culture. And that's so important and getting more important. So as a person who's been around and kind of seen the challenges, the real challenges in science, I thought it was a great opportunity to, when Soren said with Alex, why don't we do something with the Quantum Science Center? Because talk about an area where we have real challenges in conveying what's going on is quantum. I mean, all of us have our challenges with it. And so I think it's a really wonderful thing. This being kind of our third iteration, we are learning more as instructors about how to do this. There's a very interesting experience we had, and I hope we can share this with you as our speaker, graduate student Pratik Kashyap, who is from ECE and outside of quantum, but that makes it kind of interesting. We worked with him a lot actually, and saw a great transformation in his presentation. And we worked with the other students here, and Zach Martin will be presenting. It really is an interesting process of conveying how to get from A to B, how to go from a very process-oriented, detailed conference type talk to one about product and really about a story. And so we look forward to more of these, and I just really happy to be involved with this. There is an online course that has been developed, and that is on the Brightspace for Purdue. It's Engaged Science Communication, and that's sort of the playbook for this. And that's evolving also. Soren and our colleagues from Polytechnic have developed that, and I think there's great, it's really a great script for this. But it is a very interactive process. I think we can all agree that this required a lot of interaction, very social thing. So kudos to those who've done this in this challenging time of COVID. So we appreciate those guys folks working with us, and so it's, you know, it's a very social process, and we're lucky to have Soren here to guide this. Soren, I can go and introduce Pratik if you want, or if you want to circle back on a few things before we get into it.
Yeah, let's give our listeners a little bit of context so they better understand what we're trying to do here. First of all, what you will see, you know, when Pratik will present his presentation, will present his ideas, will be a little bit of a, oh, I wish, a little bit of a magic act, I wish, in the sense that there will be a before and after, right? And unlike magic acts, I would like to tell you what's in the black box, what went in the before, or what went in turning the before into the after. Both Pratik and Zach, right? They're going to be here. So what is in the box? You know, what is our method for training graduate students, especially graduate students, but, you know, if our colleagues want to go through this process, I would invite them to consider this. But especially for graduate students, you know, what goes into turning them into engaged science communicators? Okay, so the idea here is that, A, we want to help a science storyteller identify, first of all, the value proposition. Now, you probably know this from your own work. You know, whenever you sit down to write a paper, you think about the so what of the paper, right? So that, you know, the reviewers will shake their head and say, yeah, this is a contribution that deserves to be published. But when we talk about engaged science communication, the value proposition should be much, much, much more tangible, broader, and understandable to a lot more people than you usually consider when you write a paper. So the very first step an engaged science communicator should do, and this is what we do with our students, is to think about the ways in which that which they propose changes even a little bit the way we think their field, their problem, their field, and the world in reverse order, right? So we invite them to think about the way in which what they do changes, contradicts, more specifically, what the world knows about, you know, the process that they study. I know this is a very tricky process because many advanced scientists nowadays work in very narrow fields where progress is measured in nanometers, right, or picometers rather than leaps and bounds. And it's not always very easy to tell, you know, how much more you have pushed the field, or, you know, you might think about yourself as a marginal contributor that, you know, adds to the general effort. But by the end of the day, what you do and how you do it should change the world and should violate something that we know about the past in a certain way, so that, you know, your work is worth its while. I presented a couple of ideas related to identifying, you know, contradictions, or identifying ways to contradict the present state of affairs to the group of students in the past. I don't want to bore them to death. You know, probably many of them are here, but for those who weren't here, I just want to say something to this effect. You know, if you think about science as a progressive act of making new data fit, right, into a theoretical framework, you know, you probably understand that, you know, you do it not just by, you don't do it by truncating or forcing the data into theories. You do it by changing the theories. So most often what we are after is changing structural theories in such a way that they better explain the data at hand. And this contradiction sometimes is quite simple to do, because there isn't an infinity of ways in which the data fits the theories or vice versa. Mnemonically and epistemologically, from the viewpoint of the theory of science, actually at the highest level, when we engage in data validation or, you know, theory validation, what we do is we look at what we have and we try to determine if the things that seem to be many are in fact one, or vice versa. The things that seem to be one should be actually explained by many things. That things that seem to be uncorrelated are correlated, right? Things that seem not to make a difference do make a difference, and so on and so forth. So, the contradicting assumptions, in science is very much about, improving theory with new data. But then when it comes to explaining how you go about doing that, that's when things become really, really, really difficult, because what is known about the data, what counts as data, how data works, right? And what the theories are and how they work and what their specific terms are, is very abstract, has become very, very, very abstracted. And you cannot, try as you may, you cannot simply say, my predecessors thought that, the quadriceps, fields of 17th degree, were actually of polynomial higher level relevance and all, you know what I mean? Obviously, I'm making it all up, right? But, you cannot say that, because you're losing about 90% of the audience, and only, and of the 10% that's left, probably only 1% understand what you're talking about. So after you identify, what's the contradiction that you can relate to somebody that's in your field, then you need to find a metaphor that captures in the most immediate and a widely explainable way how your contradiction really works, what your contribution really is. So what I'm trying to do with our students, with our learners, is to advance them from identifying their value proposition to translating the value proposition into a language that makes sense for everybody at the same time. Now, the process of engaged storytelling doesn't stop with finding a clever metaphor to explain, what you are doing and how you are doing and how what you do changes everything. And then after you establish this common ground, then you can dive into the science and the scientific details of what you do so that you establish your credibility. So there's a part of that in my recipe as well, right? But without the metaphor, you are not really communicating in an engaged way to the world. You are only communicating to a very narrow spectrum of connoisseurs, people who know what's going on. And even among those, only very, very few can really appreciate the finer points that you're trying to make. So I'm really, struggling here, and we're struggling in a good way with the idea of bringing people to the surface and making them shout to the world their message in such a way that it's not, muffled by the water in which they were sunk up to that point. All right. So this is our method by and large. Now, there's a lot more to it. Maybe toward the end, I'll show you a little clip to kind of give you a better view of how our method of teaching works. But I think that the best way to go about this is to show and tell, right? So as we mentioned before, we worked with two graduate students very closely, and we started with their projects, the way they thought about them and the way in which they were ready to communicate to this specialized audience. And we tried to turn those otherwise excellent specialized conference presentations into something that comes closer to what we consider to be, engaged science communication. And along the way, we tried to teach them all these tricks: contradict, show relevance, find metaphor, communicate with metaphor, go back to the science, come back and connect to the real world. Okay, so let's see the magic act now. So who are we starting with, Neil?
I think we should start with Pratik Kashyap.
Yes.
From UZE. Pratik studied used MRI to study mild traumatic brain injury, and so we. Well,
let's not give too much away. Let's not give too much away.
Okay, let's not do that. Right. I just attempted,
let's not do that, because we spoil part of the fun. So Pratik, are you there?
Exactly.
I am here.
All right, Pratik, wonderful. Now, Pratik, remember, the trick here, we're going to play some tricks on your mind, right? So we're going to start with you in a state of wakefulness, right? So what I want you to do first is to give us your classical conference style presentation in the quickest, most technical manner you can, right? The way we listened to it many, many weeks ago, yeah? And let's do it with the visuals, right? So if you can bring up the screen, the slideshow on the screen.
Pratik, are you able to do it? Or
let me actually bring up the slideshow. Do we want to use the YouTube video or directly go with
the old one, you mean?
Yeah, for the before take.
Yeah, if you have it handy, yeah, we can play it. We can play it because that's, a little bit more constrained.
Yep. Neil, I believe I shared it with you. And if you're co-host, it should be easier for, I'm also co-host.
Okay. Let me get that then. I had pulled up something else. I pulled up the slides from you. Let's see here. All right, give me 1 minute here, guys.
While they do that, I'm gonna share with you all a series of videos that go form the infrastructure of my Engaged Science Communication course. They are all on YouTube, and they include about 12 short 3 to 5 minute clips that present different perspectives on engaged data and science storytelling. It starts with 2 little stories that give you a broader introduction to how everything works, and then there are the other videos. Now, okay, did you find it, Neil?
Yes, I have found it, and I'm going to try to share the screen. See if I can do that to this. And can you see the screen?
Yeah, everything's fine.
And let's see if we can
hear. So again, everybody, this is the before.
Right.
This is typical science communication.
Let me see if I can get the sound also. Can you hear his sound? Guys? Soren, did you hear the sound?
I did not hear any sound, no.
All right. I might need to consult with somebody who can help me with the audio. Alex, can I?
Let me probably try to share it, and maybe I can use my speaker. I believe we ran into the same issue in one of our meetings.
Yeah, we did.
Yeah. Let me just do that. All right, just checking the sound. Sport athletes. Is it audible?
Yeah, it works. Yeah.
Okay, yours works.
Just pump it up a little bit.
All right. Hello, everybody, and welcome to my talk, Neuromorphometric Analysis of Collision Sport Athletes. Essentially, I'll be talking about 2 concepts and applying it to a data set of collision sport athletes. Collision sport athletes can consist of any athletes playing sports such as soccer, football, etc. The concept I'll be delving into is known as neuromorphometry, which is pretty much understanding the evolution of the neurohomeostasis using a morphometric approach, or understanding the shape, intensity, and how they evolve over time and with space. Core science of my raw data basically uses the T1 weighted magnetic resonance imaging that is collected, or is also termed as the spin lattice thermal longitudinal relaxation time gained from nuclear magnetic resonance species when placed in an MRI scan. The novelty of my approach is that we'll basically be looking at morphometry or volumetric changes for a region-based study. I'll be normalizing it using my baseline MRI scan. So essentially, it's a normalized approach that gives you values that are basically relative errors in time. This essentially provides patient-specific analysis, permits longitudinal analysis, it's region-specific, and it's piloted on an MTBI data set. More of an analogy that can help us understand what exactly the math behind all of this neuromorphometry is when we apply it to the US Electoral College system, essentially understanding or capturing a country's opinion as to who should be their leader or their president cannot be determined by a popular vote. It's done using the Electoral College system that equally weights or has a representation equivalent to the United States Congress. So there's a local or spatial element that factors in that adds up to the grand mean or global country's vote. Essentially, when you look at the final output, which is the country's sentiment or who's going to be the leader, I'll translate it to the neural health prognosis. On a final level, a person's vote, because my raw data is T1 relaxation, that's pretty much what a person's vote would be. It's the T1 relaxation of the nuclei. Looking at a level higher in the hierarchy, you look at a region of interest volume, that'll be a county's representation, then a state's congressional representation will be a tissue volume, as regions of interest aggregate to a tissue, and finally all tissues aggregate to the brain to give you your final neural health prognosis. Keep in mind that the final answers or the volumes that I get are normalized volumes, so they are not a binary measure. To convert it to a binary measure like a voting policy, we need to apply a classifier at the end to make this analogy more or less streamlined between the two use cases. Essentially, that's what I'm doing. It's a spatiotemporal localization approach and applying it to the mild traumatic brain injury data set. Simple math, but it adds up over time and space to actually give you a meaningful result with a high degree of specificity and also a higher degree of detection when it comes to this pathology of mild traumatic brain injury data set. Thank you.
All right. All right. Thank you, Pratik. Thank you very much. Now, for the benefit of the audience, so this version of his presentation, it's a little bit spiced up with some metaphors. So it's a little bit of more broadly understood social, if you want, explanation of what he does. But as you could see, the beginning was very much driven by the science and the science alone, more important by the application of the science, such a way that we did not quite even see where the novel application was. And also the connection between the metaphor and the novelty of what he does was relatively loose, right? And by the way, there was another version that had absolutely no metaphor in it, and probably we should have given you that raw, just to kind of give you an idea of where we started. But that was the before. Now let's try to take a look at the after, right? You know, at a presentation that focuses from the get-go on the metaphor and on contradicting what we do and we do not know, and then continuing with the science and coming back to the relevance of the research for the world outside. All right, so Pratik, are we ready for this second part?
We are ready. And
absolutely. Well, I'll give it all to you now.
All right, thank you. Folks able to see my screen?
Yes, we can.
Alrighty. So hello, everybody. Pratik Kashyap here. I'm going to talk to you about something that is very close to my heart and constantly drives my mind. It is about quantifying safe standards for athletes involved in collision-based sports with the broader goal of understanding their overall brain health. Let's look at the numbers first. An average adult human brain has about 86 billion neurons with over 100 trillion synapses or conjunctions, especially in the cerebral cortex. Modern imaging captures these macroscopic behavior of the brain at a sub-millimeter resolution to help us understand the neural dynamics non-invasively. Communicating the intricacies of my methods can be best done by exploring this analogy of measuring the brain as if it were a country. The number of people in a country is a few orders lower than the number of neurons in the brain. Gauging the opinion of the people can be similar to quantifying the neural activity in the brain. A brute force approach to measure a country's opinion, say the United States, would be to elect her president using the national popular vote, as opposed to the Electoral College's approach that factors in a spatial factor, which is the representation of the states in the United States Congress. A grand mean aggregate doesn't give us the right idea, as it doesn't factor in the local diversity and specificity. The method I propose does something similar, in the sense it does not allow a bias from the regions of the brain or the country to overpower the true spatial diversity of the underlying change. Here, the change is being quantified by the study of morphometry for a neural setting, aka neuromorphometry. A direct application of my algorithm to the Electoral College symbolic analogy can be brought about by introducing a binary classifier to the region-specific local volumes that I do calculate for the brain. The political diversity of the people is not simply captured by just the spatial specificity. States evolve over time to be divided and in some cases swing their opinion from one party to another, which can very well decide the final vote. Quantifying this longitudinal change is another novelty of the method that I propose. Combining the spatial specificity and temporal evolution of complex systems and measuring them using my method via a normalized approach provides us with a deeper, more finer understanding of the underlying phenomena. Here, I have demonstrated my algorithm to quantify the regional volume change of brain tissues for athletes involved in collision-based sports such as football and soccer. Essentially, it promotes patient-specific and region-specific longitudinal analysis on this mild traumatic brain injury dataset. Delving a bit more into the core science of my raw data, the T1 weighted magnetic resonance image captures the spin lattice longitudinal relaxation of the nuclear magnetic resonance species for a three-dimensional grid at a sub-millimeter or 1 millimeter isotropic resolution. Different tissues have different T1 relaxation values, thereby helping us to understand the biological distribution non-invasively as opposed to post-mortem analysis on a Petri dish. And finally, a glimpse of my primary application. The need to study this pathology and drive more research to understand it better is driven by the fact that about 50 to 90% of these hits, whiplash, trauma of various forms to the head and body go undocumented, close to the number of voters who don't cast a ballot. They are only recognized when they present with any symptoms, which in most cases can be too late to mitigate permanent, long-lasting chronic change. My method helps us capture these changes with a higher degree of spatiotemporal specificity and helps us inch closer to a solution using neuromorphometry. Thank you to my advisors, my family, friends, and colleagues for supporting me every step of the way. This has been a really enriching experience, and I thank Soren and Neil for including me in their pilot.
Thank you so very much, Pratik. This is very good. Thank you. Appreciate it very much. And I hope that the audience appreciate it as well, you know, how much better and how much more integrated the story has become as you try to put that which was more immediately communicable and understandable first, and the science not second, but the science in the role that it needs to play, which is that of supporting, you know, your broader idea and the difference you make. Probably this is the thing that struck me the most when I listened to your second iteration, which is that science, although it's very important, you know, it plays a different role. It's not an incantation anymore, right? Science is not just a way to to talk to a limited number of people, but to convince everybody who listens to you that what you're doing is legitimate, is rooted in serious research, and your novel approach is not only interesting but justified. Okay, right. One other point I'd like to make is that in between the two versions, pretty advanced between a presentation that very initially was called Neuromorphometric Analysis of Collision Sport Athletes, right, to measuring the brain as if it were a country. So in the process, what we did and what we worked really hard on was to switch from the science to the metaphor right off the bat, okay? All right. I'm wondering if we have any questions at this point, any observations, any perspectives on what we're saying. I want to make sure that we have not lost anyone along the way.
So far, I don't see any questions in our chats, but
okay.
Probably they will come later, and then I will let you know.
Okay. All right. Well, hopefully, the points we made so far are very clear. Just to recap, our method of teaching engaged science communication relies on identifying value proposition, translating the value proposition in a very abstract proposition where you're trying to figure out what exactly are you doing, how are you changing the world of knowledge by saying that what was considered to be one is many, what is many is one, what's correlated is not correlated, and so on and so forth, and then applying this basic fundamental explanation to a metaphor taken from everyday life knowledge experience, and then providing this to your listeners as a key to understanding what you are doing in your day job, so to speak. Okay, now let's invite now Zach Martin to go through the same process. Now he is much closer. His area of research is much closer to what you guys do, is an emerging quantum scientist and quantum engineer, right? And again, like before, we are going to go through the two phases of his work. And we're going to start with version 1, which actually in this case will be devoid of any metaphors, right, Zach?
Yeah, these are just sort of the preliminary outline slides that we've been working on. So the first step is actually quite unpolished.
Yeah, but which is okay, because they're unpolished in one way, but at the same time they're a very solid presentation of a scientific project. He will not BS us, right? He believes every single word in what he said here. So Zach, take it away. You're talking. Sure. We're talking now. Science. Go ahead.
Can everyone see my slides?
Yes.
All right. So my first title was Making Quantum Light with Metal, or Plasmatics for Indistinguishable Photon Generation. So the big question with a lot of the quantum technologies that we're developing is, well, why do we want to use quantum in the first place? What advantage do we gain? And in a lot of ways, the development of quantum computing and quantum information protocols mirrors what has happened in the past as new technologies replace old ones, such as steam power is replaced by the internal combustion engine. And in the last century, analog computing was replaced by digital computing and integrated chips. So what we're finding now with current computing technology is that there are limits to Moore's law. There are limits to the number of transistors that we can fit on a silicon integrated chip. And there are also limits to fundamentally what classical computers can do in a reasonable amount of time. And we see for that certain types of problems, and for certain types of problems that are especially important, such as just designing new materials or discovering new drugs, quantum algorithms can run millions of calculations at the exact same time. So there's an exponential speed up over classical computing. So then the big question is, well, why have we not achieved quantum computing yet? There are some promising developments, but so far we don't have this million qubit operating threshold that you need to really truly see quantum advantage for the types of problems we would like to solve. The answer really is that quantum states are incredibly fragile. They're very sensitive to fluctuations in the environment. And this also depends on the type of qubit. And there's this interesting paradox that was pointed out to me when I first started working with quantum computing, is that for the types of qubits that you have more control over, such as the superconducting qubits that Google and IBM use, trapped ions, such as at Honeywell, or solid state defects, which is, I bolded that because that's what we work with, the less time the quantum state is preserved. That's because if you have more control over a qubit, that means it interacts with either magnetic fields or electric fields more strongly, so you can control the state more readily. But that also renders it more sensitive to the environment. However, if the qubit doesn't interact as strongly, i.e. the quantum state is less fragile, it lives for a much longer time, that means you have less control. And the example that I would use for this are photonic qubits, because once you initialize a quantum state and you encode that into a photon and send it off, it's just going to keep flying and it's going to stay in that state until it interacts with matter. And so the overarching goal of our research is to marry light and matter qubits to get the best of both worlds. And to do this, we want to enhance the interaction between light and matter. And so how do we do this? How do we enhance light-matter interaction? Sometimes this needs to be pointed out to people is that light and matter actually don't usually couple very strongly. One example I bring up is the defect center that we've worked with quite a bit, the nitrogen vacancy center that lives in Diamond. Its native lifetime is something like 20 to 30 nanoseconds, which is, for a time scale of atomic defects, is actually quite long. So we take advantage of a phenomenon known as the Purcell effect. The Purcell effect tells us if we modify the electromagnetic environment around the defects that we're interested in, we can enhance the rate at which they give off photons. And we in particular use nanophotonic structures to do this. So the Purcell factor, which is the number of times that you've enhanced emission of photons to the far field, scales roughly by Q over V. So Q is the quality factor of whatever structure you're working with. It's a metric that engineers use to quantify resonators divided by the volume. And so what's really great about plasmonics, and that's the primary approach that we follow, is it allows us to create cavities that have very, very, very small V, something on the order of nanometers. So we can really shrink down the cavity volumes to quite a small size. And we have some theory that shows that the careful design and careful consideration of a certain geometry of plasmonic nanostructure in principle allows us to achieve up to 1 million times lifetime shortening. This is sort of in the ideal case, what we've shown in experiments, and we have some experiments where we've achieved even faster emission than what's shown in this paper, is by coupling the nitrogen vacancy center, a defect that we're interested in, we can achieve really dramatic lifetime shortening. And we can even modify the structures during the experiment to shorten the lifetime even further. And so, okay, so how does this make qubits? How does this relate back to what we were talking about before? Conventionally, to preserve quantum coherence or to prevent quantum states from breaking, you cool down your defect to something on the order of 4 Kelvin or liquid helium temperature. And in some cases, you have to go all the way just above absolute zero. And this extends the coherence time. It extends the time that the quantum state lives for without breaking or without the phase being lost. So our approach is actually to not worry about the environment. We're trying to operate at room temperature, or at the very least above 4 Kelvin, so that the environmental noise is still present. But with plasmonics, with enough lifetime shortening, we can actually beat dephasing processes. So we can enhance the emission such that it's so fast that spontaneous emission or emission of a photon occurs before dephasing can even happen. And if we can achieve this, what that means is the quantum state of the emitter is the same every time that it's excited, and the photons it produces are indistinguishable. And indistinguishable photons is a really, really powerful goal, because it has been shown that you can do optical quantum computing with just linear components. So if we can produce indistinguishable photons at room temperature, we can achieve optical quantum computing at room temperature. And so going forward, we're going to capitalize on some of these nanophotonic geometries that we've shown have very substantial lifetime shortening. And we're going to work with defects such as the silicon vacancy center in Diamond that have some of the best optical properties that we know about. So yeah, that was what I have for my first presentation.
Thank you, Zach. So probably a very reasonable talk for a quantum conference, and so Soren and I worked with him on a few iterations. Soren, did you want to say a few words about that? Oh, I think Soren is muted somehow. We can't hear you.
Oh, I'm sorry. No. You know what, Neil? I don't want to put you on the spot, but maybe you would like to say a few more words based on your own experience with Zach and working with him to introduce his next spiel. I can add a few words after that, but maybe you would like to say something.
Right. So, yeah, Zach was stayed with this. You know, we had an initial group, a little larger, and I think it was one of the learning experiences I had with this, and I hope that it's been rewarding also for Zach, though, is that it's been the connection point from getting from A to B, as far as making a conference talk and making a good story, and identifying the elements of story is really challenging. And that's what we're learning how to do a little better. And trying to codify this is frankly hard. I mean, you have a charismatic personality like Soren who can bring this across. And again, this is all social, right? It's a very social event here. And look at me, I'm being unsocial by not showing myself here. Now here I am. This process is a very, I think it will be much, it will enjoy a better success when we're back in person and can do this as in groups, in small groups, because this is a process of iterating, going several times through and figuring out what it is that really is the driving question. And one of the things that I think about in terms of, this is always a question we have as in science. We hear Soren talking about transformation and violating assumptions, and there's always this interesting resistance to it. And what I think is really interesting is that you look at the incremental process of engineering that happens. For example, you have small steps that taken, but there was a step that was taken at some point. They put a steam engine on wheels, right? Those things existed, but they put it on wheels, and then society was changed, right? So understanding how we violated something sometimes isn't even clear at the moment. And so learning to uncover that and say, okay, this has a promise of doing this, or this can transform. To me, there's a very interesting aspect of this, that we tend to be very detail and process oriented, as I said earlier. But what we can learn by stepping back further out of it, and going back in, is that we can find out what it is that is the real new aspect of it. So I look forward to hearing Zach's second take on this. If you want to pull that up, Soren, I don't know if my perspective is as a scientist, right? So I'm a little bit on the fence of this, but I'm really interested to hear Soren's.
Yeah, well, I'll say probably a few more words after Zach presents, but I would like everybody to refocus their attention a little bit on Zach's presentation, core idea, the way he presented it just a few minutes ago, right? For example, if we look at the first slide here, we see that now the presentation is called Making Light with Metal, a high-speed camera for quantum states, right? So right now, we have, at this point, we have a metaphor. Now, Zach, do you still have the other slide handy? I'd like
yes, I do.
I'd like to bring people back to the past a little bit.
Okay.
Because, the first iteration.
I'll just pull up the other.
Yeah, you don't have to make it a full screen, just, you know. So the first iteration, you know, was called Making Quantum Light with Metal, Plasmonics for Indistinguishable Photo Generation. Now, you probably understand what he's talking about. You're all distinguished quantum scientists and all that, but there's no metaphor in here which prevents anybody outside this room from understanding, even starting to understand where Zach is taking us, right? Now, the new one, the new version, you know, has a core central hard-coded metaphor, this high-speed camera, that will help us, you know, first connect his ideas to a more common understanding, but also, as you'll see, will allow him to dip down into the science again, all right? So, Zach, let's take it for a second spin.
All right, so. Oh, shoot. Can everyone see?
Yes.
All right. Okay, so as Soren said, this presentation is about making light with metal, or a high-speed camera for quantum states. So my research focuses on the optical properties of solid-state defects in materials like diamond. So for instance, one of the defects that I'm interested in is the nitrogen vacancy center in diamond. And what's really fascinating about these defect centers is that they can have quantum properties at room temperature. So what we would like to do is we would like to explore these quantum properties, in particular the types of light that they can give off. And we want to see what kinds of quantum states that we can encode into these defects to develop new technologies like for quantum computing or for quantum information. However, the biggest problem that we have right now is that quantum states, as my title says, are quite delicate. So if we have our state here that our defect is encoded in, any kind of interaction either with external electromagnetic noise or with vibrations in the quantum lattice due to thermal energy is going to lead to a process called decoherence. So the quantum state is going to be changed, or the phase that we've encoded is broken and we've lost the information. And so this is actually a really big problem because now we can't use the quantum state that we've prepared for computing or any other kinds of interesting studies. And so how do we get around this? The typical approach to being able to see quantum states, being able to preserve the quantum state, is we take the defect, and the material here is in diamond, we encode the information in it, but first what we've done is we've put it in a cryostat, and we've cooled it down to very, very cold temperatures. And so what cooling this down does is before we still had this noise or this interaction due to the environment, but by cooling it to such low temperatures, we've blocked the interaction. We've slowed the environment down enough that the decoherence processes don't occur as often, and we've extended the lifetime of the quantum state. But from an engineer's perspective, this is actually a bit less than ideal because cryostats are large and bulky, they take up a lot of space, and you need to use a lot of energy to cool them down to such low temperatures. So we would like something a little more elegant that can be scaled up a little bit more easily. And so again, we take our quantum defect here, we encode some information in it, but now we're operating at higher temperatures than you would use in a cryostat. Ideally, we would be at room temperature, and we're just not going to worry about the environment as much. And what our research right now focuses on is the equivalent of building a high-speed camera to capture this quantum state. And it's going to be so high speed that it's going to capture this quantum state before this decoherence process, this noise interaction, can even occur in the first place. So just to put this in a little more theoretically rigorous ground, this part of the diagram shown here on the left is kind of the conventional approach that you would use with a cryostat. You have your emitter that transitions from an excited to a ground state and gives off a photon. And by cooling it down to cryogenic temperatures, what you do is you extend what's called the dephasing time. So this T sub def right here. So that time is, as I said earlier, the lifetime of the quantum state, the time that it lives before it interacts with the environment and the information is lost. However, the option that we're pursuing here is called plasmonics. So I'll explain that in a little bit more detail here in a second. But with plasmonics, what we're hoping to do is not to alter the dephasing time, but rather we're going to take the time that the defect lives in the excited state and reduce it so that the defect is going to give off a photon before dephasing can even occur in the first place. And so if it gives off this photon before dephasing can occur, what that means is the quantum state of the emitter is the same for every photon that it gives off. And this produces what are called indistinguishable photons. And this is really, really important for quantum computing, because if you have indistinguishable photons, you can do optical quantum computing, and you don't actually need all that much. You really don't need very complicated components to do optical quantum computing. And the goal, of course, for this would be to generate indistinguishable photons at room temperature, because then this enables actual room temperature quantum computing. So what do the actual high-speed shutters that we're building look like? So these are the kinds of nanophotonic structures that we're working on. This geometry here, shown on the left, is called a nanopatch antenna. What this consists of is a silver mirror, an insulating spacer, and a silver cube. And then the diamond that contains our optical defect is situated right between them. So what this does is it traps the light from the laser field that we use to excite it, and it confines it in a very small volume like this. And then another geometry that we're exploring is called a plasmonic launcher. So basically what we do is we coat the entire diamond with a silver layer, and it couples light to a type of surface wave. And these geometries, these nanophotonic structures that we're building, enable us to take advantage of something called the Purcell effect. The Purcell effect tells us if we modify the local electromagnetic environment surrounding our defect, we can enhance the rate at which it gives off light, that rate of spontaneous emission that I showed a couple of slides back. And what's really nice for us about the Purcell effect is that this Purcell factor, the number of times that we can enhance the emission, scales inversely with the volume. And plasmonics is perfect for this sort of approach because it scales inversely with the volume. So what we've shown in theory here is that by careful consideration of the gap or structure parameters, we can achieve up to 1 million times lifetime shortening. And this is taken from a paper that came out last year. So we do see that in experiment, if we couple the defect center to these gap plasmon modes or this nanophotonic structure, we can achieve actually quite substantial lifetime shortening, something on the order of 4 to 5 times. And we can even modify these structures further to shorten the lifetime even more. And so this is still an ongoing effort. We're still working on using different kinds of structures and different types of defects to produce indistinguishable photons. But it's quite promising because, as I said earlier, this would enable optical quantum computing, and not only optical quantum computing, but room temperature quantum computing. You wouldn't need this bulky, expensive cryostat equipment, and you could scale this up to build something like a quantum internet. You could have practical large-scale quantum communication. And quantum computing is also really exciting because for certain classes of problems, you can solve thousands upon thousands of equations simultaneously. And this lends itself really well to problems where quantum effects are quite strong, such as in designing new materials or drug discovery. So this is something that really could be as groundbreaking or as world-changing as the steam engine or the internal combustion engine. So that's what I have. I'd be happy to take any questions. I'd really like to thank Soren and Neil, obviously, for all their help, as well as Alex Senechev for coming up with this metaphor in the first place, as well as the rest of the Purdue Quantum team.
Wonderful, wonderful. Thank you so very much, Zach. Very to the point, very short, very cool, very inspiring. I'll give you the job if I had one. Now, I'd like to remind the audience again that what we're trying to do here is not to turn our apprentices into that which they are not, but to help them sell their wares to a broader audience. And that's why, to a certain extent, the two types of talks were similar, but in some vital aspects, they were different. Now, a final observation is that, this process that we worked on with Zach and Pratik can be calibrated as needed. Now, for the purposes of this conference, we kept the science pretty sophisticated and complex level, because we do not want to disappoint anybody. But things could be dialed up or down as needed, such as that if you are going for a job at a pharmaceutical company, you know for sure that there's only one quantum scientist in the room. You don't want to go too deep, so you'll keep it higher and you'll talk the metaphoric language a little bit for a little bit longer. Okay, and with this, I would like to stop and take your questions, observation, comments, or anything you might have to say about this. At the very, very end, again, I'll share some more resources with you in case you're interested.
Yes, we have a question from the audience. Pratik briefly commented on this already, but I would like to read it out, and maybe you, Zoran, and Neil could provide more details. So this is regarding the first student presenter. There is a feeling that this is a matter of really knowing the audience. For example, you're not suggesting to present in a second way during the physics conference. Meaning the same, my understanding, topic, but now to the physics conference. And is it correct that your techniques are more for non-experts?
Well, yes and no. Yes, because I don't want to upset anybody. No, because I really think that even scientific audiences are quite diverse themselves. And there's a lot of, how should I put it? There's a lot of new knowledge that needs to be translated before it can make its fuller and deeper impact on the world. Now, for example, let's talk about Pratik's method. He comes at the problem from an engineering perspective, if you want. Maybe, much of the science he talks about is not as exciting and all that as some people can think it could and should be. But at the same time, if he were to give his talk strictly at a very strict scientific level in a scientific environment, the impact that he does on his scientific audience might fail to make the mark that it should make, that he is really changing the rules of measurement game, right? Measurement, we never think about measurement as fundamental contributions, but sometimes they are, right? So, I would encourage you actually to think very deeply and carefully about, the ways in which you try to overcome the limitations of your very narrow field. Now, if you go to one of these conferences that has superstars in it, especially the people who have made really big names for themselves, you'll notice something very interesting. Very often, they try to break the mold. They try to tell the bigger story of what they do by telling jokes, right? Why wouldn't you, follow their lead too? And why do you think they do that? I mean, they don't, they are as adept at the science of it as anyone else, right? They know the science as anyone else. Why do they need to, make those jokes? Well, they need to make those jokes, not because, they are not believed, but because they are trying to penetrate through the veil of, pretend knowledge, not to call it ignorance.
Yeah, that's great, Soren. If I could add a little bit from my experience, and I'm sure the professors would echo this also, that you go to a colloquium, even if it's a department colloquium, and everyone in their room is a physicist. Invariably, the first 5 or 10 minutes of that colloquium are where everyone's tuned in. Then the speaker sometimes goes into warp speed and they go beyond. But I always found those first 5 minutes to be where the interest is, and that's where where you're getting into the concepts, and going slowly through that, stepping, even if it's to a specialist audience, if you're going to step back and take it from a new perspective, that's very fruitful, because it'll help you to rethink it. It'll help your audience to see things that you probably assumed everyone knew, and they don't. And that's the interesting thing, is there's a lot of less consensus on things than one would think. And so, yeah, this going at the higher level, at least to approach it from the higher level at first, is a very it's a very fruitful thing to do. And then you're going to be writing proposals to people who are going to be reviewing them. And they're not going to want to hear you talk fancy. They're going to want to hear you talk to them and compel what you're doing is important. It's going to change something. And that's what it's really got to come down to. And that becomes the habit of these people who are really great speakers. And I think Professor Boltaseva and Professor Shalev are both examples of that. When they give their talks, they compel something in their research that the audience can relate to. And so that's a very big learning experience for people who go in to start writing grants, is they realize, well, okay, this committee is not going to be wanting to pore over my research and really work their brains out. They want to get it. They want to get the message easy, and they want to be compelled by it on the first page. So those are very important reasons to remember this. That is your style, to take this into your style of presentation. So just adding on to what Soren was saying there. So if we have any other questions, Alexander, did you?
No, at this moment we don't have any further questions, so we can continue with the next part.
Okay.
Okay. Well, I don't have much more to say, tell you very honest. I don't want to bore people to death after, we listened to these great examples of transitioning from pure communication, science communication, to engaged science communication. The only two other details that I would like to add is that our materials are online. Again, we have this series of video clips that give you several ideas as to how to massage your presentations, how to work with them. We have some tips for utilizing color, shape, and imagery that some of you might find useful. There are a couple of modules that speak about ethics and how ethics should be a part of the scientific process. Now, obviously, when you're a material scientist, sometimes you don't think about ethics, but there are always implications for just about everything we do for other people, for our life together. And you need to think about the ways in which the materials you'll create, the algorithms that you'll create might change the world. I provided that link in the chat, and I'll ask Alex to share that with you by other means. And also the full complement, the classes that we offer, I offer, and Alex, Neil, and I offer can be found at this link that I'm sharing with you here now. And yeah, and that's about it. It was a pleasure to listen to you all. And unless you have other questions, I guess we can, take in abeyance.
Yes, if there are any questions, feel free to type them or raise hand and communicate with any mean you're comfortable to.
I'd like to just offer one thing as a resident there at Burke, and I know this QSC is beyond Purdue, but I'm obviously very invested in this, and I know some of you graduate students are getting to later on in your PhD, and you're going to go to interview talks, and that may be a time when really this kind of thing will resonate more. I'm happy to offer my help and feedback and translating this course that's there online, and to provide you feedback for talks, and bring whatever you have. You know, we enjoy seeing the transformation. You don't need to bring a perfect finished talk. I want to work with people to so that you can see an improvement. And so I'm there at Burke, and I hope that my information is also shared in the summer school. You know, it's really a passion of mine to help out here, and you know, this starting along this science communication road with all you. So just wanted to offer that up too. So.
All right. Of course, yes, we will share the information with all attendees, links to video and online course, as well as your contact details. So if anyone has more questions or comments and would like to reach out to you, they would have this opportunity. So if there are no other questions, I would like to thank you, our speakers, again for the wonderful workshop. And I hope everyone enjoyed it. And I would like to thank all the speakers of today's session and of our first day of the Quantum Summer School. I also hope that you enjoyed all the presentations. And thank you, everyone. And we are looking to see you tomorrow for our second day. Thank you so much.
All right. Thank you. Thank you all. Goodbye.
Thank you. And with this, we will conclude.